Hello, 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 hello.
हाँ जी। Is that better? Yeah. Sorry. Sorry to the online people. Yeah, so this is just this gadget here. So finally, if this was a plus b and then you're just adding another one, you can see this is just the primitive recursive definition of addition. Is that a bit clearer? Okay, yeah.
So I'm just did can't call the UL and UR rules. Are they specialized for every data type thing, or are they generic?
They're generic.
You don't show them?
I showed them last slide.
Okay.
So they're literally these ones here.
Oh, okay.
Right. So for every format, yeah. So the right rule is just like an in. You can think of it like an in for inductive types, and this is like the iter of inductive types. Okay. Yeah.
So here the implication sign you're using as sort of the combination of the population implication and the design.
So this is just syntax. So if it's like the turnstile if you're working in natural deduction with explicit listing of hypotheses.
So you have a separate implication for like on the right if you want it.
Yes. Yeah. There's an arrow type. You can think of this as turnstile if you're more comfortable. If in intuitionist logic, it doesn't make a difference. Yeah. Is there an adjunction?
Between the muse and the muse?
I'm not comfortable enough to answer that question because, yeah, I don't know. I think it depends on the semantics, right? Because there are two. Okay, so we'll get into this, but this is one interpretation, but there's another interpretation where if you're working in like the complete lattice of some candidate saturated sets, for example, then you can also interpret these as bona fide fixed points, and then maybe I don't know if they would be an adjunction in that setting. So I think it may depend on the semantics. Well, maybe not. I don't know. I'm actually not. It probably is independent actually. But I just want to show another example because I think inductive types we're kind of used to working with NAT, and I think many people will also be used to working with some code data. And so here's one example of code data, and this is meant to be streams, in particular streams of natural numbers. Okay, so how is this type? This is the greatest y that's closed under taken product on the left, right? And you can think of this as kind of giving you a way of extracting heads and tails of a stream, right? So every stream has a head and it has the remainder, which is again a stream, right? And in that sense, we can find derivations for head and tail, right? So the head is just a function from streams to nat. So I have streams to nat here. And what does it do? Well, the new left rule is symmetric, right? So it's just like, it's an out. Instead of an in, it's an out. And it unfolds the fixed point. And it says, okay, so you've got a stream. Let's do a case analysis on it. It has a head and a tail. What do I want to look at? I'll look at the head, and I'll just return the head. Okay. And tail does the same thing, but takes the right summand, right multiplicand. Okay, so this may look a little bit unusual because I'm working on the left in a sequent calculus style, but you can also think of this as kind of rotated 90 degrees in a natural deduction style. And the reason is because I want to use a different system later. And then here's just another example, which uses some co-iteration that just takes a natural number to the stream that just repeats the same natural number. Okay, so what does it do? It takes this nat and it wants to return a stream. And in fact, what it does, if you remember here, this was the recursive call. So now this is going to be the co-recursive call, right? And the co-recursive call is just going to say, wait, was this a typo? Should this be a? Yeah. Sorry. This is a typo. Yeah. No. Hold on. No. It's not a typo. This is fine because it's an invariant, right? So this replaces y by invariant. For the invariant, I'm using n, right? But I think no, because it's an invariant. You plug y into here. So n is my invariant of this fixed point, right? So I need to show that n is a post-fixed point. Okay. Okay, but okay, maybe there's a typo up here. Maybe I can't remember, but I think for the interest of time, I'll move on. Okay, but yeah, it's important to say like this is not just unfolding the fixed point on the right, and the mu doesn't just unfold the fixed point on the left. You have built-in co-recursion and recursion. But there will be another system that we'll look at where we do have such things. And somehow, so I've kind of been informal about the semantics, but one way to think about this very, very formally, if you're familiar with the sequent calculus, is that you have this notion of cut elimination. And this can be seen as an actual semantic. So if I have a function, for example, of this type, n to n, and I feed it some actual inputs, I cut in some numerals, then cut elimination will converge and actually give me a numeral output. And that formally can be seen as a semantics. Okay. But now I want to talk about a different style of system generated from the exact same syntax. So I still have sequence built up of the same type language that I had before. But now, instead of looking at just well-founded finite derivations, I want to think about potentially infinitely deep derivations, right? So think of something like, infinite lambda terms or infinite rewriting theory. So seen as, if you see the type system as a polynomial functor, I'm just going to be looking at those objects that are co-inductively generated from the typing rules. Okay, so this is, in this setting, some conventions, I don't need, it turns out I'm not going to need the iterators anymore, or the co-iterators. Instead, I'm just going to replace them with unfoldings. So in which case the derivation before, when I had the new right rule, it would have to keep the S around because I only have unfoldings. So at the moment, of course, if I only have unfoldings, there's nothing syntactically distinguishing least and greatest fixed point. You're just saying they're both fixed points. And so the key idea in this line of work is to look at a global correctness condition on these typing derivations that distinguish these fixed points. And why is this interesting? Because we're particularly interested in this kind of fragment of well-behaved ones, which are the regular co-derivations, where you have only finitely many distinct sub-co-derivations. So why is that interesting? Because it means you can write it as just a normal graph, finite graph with cycles. So it looks a bit like a machine model, right? When you have loops in a machine model. So it brings your notion of typing derivation much closer to machine models. And this is not this is not a new idea. This has been explored by several authors for the last 15 years or so. Well, I will skip that perspective. So, but let's see some examples. Right, so let's see addition again. So we saw this function before, but now here's a different program for it that looks a little bit different, and you can see it as a bit more fine-grained. So it looks at this n. This is the a, the first argument. And this time, you're just doing case analysis, right? So it just says, well, n, okay, you're 1 plus n. So in the case that the n is 0, it's just doing the same thing as before. That's the same as before. But now, the semantics of this is not that this becomes the recursive call. This just becomes, if this was a plus 1, then this is actually a. Okay, the semantics doesn't do any recursion. It's just doing case analysis on this new rule, right? And so you have to get the recursive behavior from something else. And instead of the typing rule, it will come to some kind of looping in the proof structure. Okay, that's where the recursive behavior will come from. So now we had a plus 1 and b. We followed the rules, and we're back to a, b here. So what did we do? Well, this was just the gadget for successor. So it applies a successor, and now I've got a and b here. This thing is going to be 1 plus whatever this is. And what's this going to be? Well, recursive call, calculate it. Does this make sense? So now the example now is, instead of like how you might program this in, say, primitive recursion, is how you might just program this in something like a Turing machine, right? Or another programming language, right? So this is the idea. So it's a slightly different kind of paradigm. Okay. Yeah. You're asking, why do I know that it terminates?
This alternative way of doing addition, is this what is happening here? When you're writing the right hand side as 1 plus n somewhere up.
The right hand, this side here.
Yeah. So
this is an unfolding of this fixed point. So this is just the successor gadget.
Of the sum.
Of the right hand side. Oh yeah. But we don't know what the right hand side is yet.
Exactly.
We have to compute it.
Right.
But yeah, so in the meta level, I know that this is computing addition, and if I know it's computing addition, then I can prove I can prove this computes addition by using that as an invariant. Yes. So if I know that this is the sum of a and b, then I can show that this is going to be the sum of a plus 1 and b.
Right.
Yeah. So so you can use that in reasoning to prove the recursive properties of addition of this derivation.
I guess the challenge is to take this gadget and know modularity of this gadget and where you plug back this circuit.
When you're designing the proofs, to some extent, yes. I mean, but we can. There's also a result that from any typing derivation in the first paradigm, you can translate to one in this paradigm. In fact, the more difficult thing is going the other way around, which is the idea, which is
Which
just
is like trying to find the violent program from using something with tokens.
it's
almost that.
thematically similar. Like quite a bit more precisely, it's like trying to find invariants for this. So Abhishek's question was, how do I know this? Well, my paraphrasing of your question is, how do I know this computes addition? Well, I constructed an invariant in my head, right? But in general, how do I construct the invariant? So it's that direction that's less obvious. Okay, good. And then let's also see this some examples on streams again. And so we've seen this function before. And remember, before we did have this s went to n times n because it was an invariant, right? We were just showing that n is a postfix point. But now we're just unfolding. There's no infinitary things going on here. It's just a simple unfolding. So I want to map n to a stream. And so what does it mean to map it to a stream? I need to tell you what the head of the stream is and what the tail of the stream is, right? So based on n, what is the head going to be? It's just going to be the identity. And then based on n, what's the tail going to be? Well, go back to the start and repeat, right? And this is a slightly more interesting one. So this is an interesting one because all these have been regular proofs in the sense that you can see there's only finitely many distinct subproofs. This one is identical to this one. But here, this is a non-regular one. So if you have an actual stream, right, and possibly irrational stream, so it doesn't have to be a rational number, then this also has a co-derivation. It just won't be regular. If the stream is rational, then this will also be regular, right? And all you do is just got s on the right-hand side, and just for every position in the stream, you're just printing the numeral that lives in that position, okay? And that's a bona fide co-derivation for us. Okay. And you can kind of also see that this is also a well-defined stream in some sense. So at the moment, something that's not that we've obviously lost because we have loops is that programs don't always terminate, right? They're not always total. But the ones you see here all are well-defined on all inputs, right? So let's say something about that. Oh, I think I said something about that before, right? So right, so sorry, maybe I didn't emphasize this. So we have this correctness condition that I'm not going to get into, but maybe one thing I should say is that this is, if you are Abhishek's talk, it's really the same correctness condition. We're asking that every branch satisfies some omega regular property. So every branch is recognized, lives in the language of some Buki automaton. So in particular, it's a criterion at the level of the formula occurrences. And you're asking that an infinite good object exists for every branch. And so the main thing I wanted to get to in this talk is this question, which is, okay, so we have these systems. Mu J was the first system we saw, and C was the circular system. I kind of waved my hands and told you that it's very easy to go from mu J to C mu J, but what about the converse? And in particular, what functions can you represent? So I have a type system. What natural number functions can I represent? So that's a very robust question. Maybe at higher types it's less robust. It depends on the semantics you take. But at least for natural number functions, what do these represent? So it's a very kind of classical question. And this question has popped up in the literature repeatedly in the last 15 years by people like Beld, Miller, Sorin, Duman, Day, Heath. There's a lot of people, and Claire Hombault and people like this, also for other logics, like based on linear logic. Maybe there's a few things to say here, like it's not obvious how you would answer this question. So there's some inherent impredicativity going on in these fixed points, and that's kind of from the second order encodings, right? If you see them as a fragment of system F, then you can see there's some impredicativity. And that's really coming out of the fact that I can have fixed points whose variable occur under two implications, right? So you don't have a set theoretic model here, like you would in something like dependent type theory. I already mentioned this. The natural guess is that circular typing should give us more functions because it's very easy to go one way, but it's not obvious how to find the invariants. And finding this progressing condition that I've not really talked about, the correctness condition, is quite subtle. And it's a p-space complete property, and it's not very easy to manipulate. There's a lot of infinitary combinatorics. So maybe the main thing I wanted to get to was this slide here. It was just kind of a flash of our results. So this looks a bit scary, but actually, how much time do I have?
3 minutes.
3 minutes. Well, I was interrupted a little bit and we started late. Let's say 5 minutes. Okay. Okay, so I've got a load of extra slides of details, but I won't do that. Instead, I'll just say a little bit about this slide, and then we'll do some conclusions. So the main thing is that we showed that these two calculi that I already just explained to you, it turns out they do compute the same first order functions, somewhat surprisingly, but not for an obvious reason. So like I said, one direction is quite easy. For the other direction, you can see there's quite a long detour. There's many steps, which is meant to scare you. And in particular, we know what the functions are. They coincide with those functions that are provably recursive in a particular fragment of arithmetic that we understand. You don't have to know what it is, but it's called pi12 comprehension. But just for reference, this is one of the strongest theories for which we have an ordinal analysis, a proof theoretic analysis. So it's very, very expressive. And for context, beforehand, the best bounds we had on this were things like system T, which are very weak indeed compared to a system like this. So these systems ended up being a lot more powerful than we thought they would be. And a way to parse this diagram is if on the bottom here, we just have proof systems or type systems. So these ones are already seen. This is just some kind of negative translation that helps the rest of the argument. But the key things to look at are these purple arrows on the sides, because this takes us from type systems to mathematical theories. So we're really leveraging on a lot of kind of classical links between proof theory and programming languages here. So maybe two of the most interesting things here are, for the circular calculus, we actually give a semantics where we can say formally that the denotations of these proofs are total, and not just total, hereditarily total. Right? So for this, you have to come up with some kind of, you look at, if you've seen semantics of system F, you look at these saturated sets, a notion of a good set, a candidate, so a set of untyped lambda terms that has good properties like closed under reduction. And you can use that to formulate, to come up with a kind of type structure, a higher order computability model of this calculus. An interesting thing here, yeah, go on.
So what's the minus?
I'm working in the negative fragment.
Okay.
Same here, same here. These can all be interpreted in all the strongest possible ways. So the whole fragment maps in CMLJ, but this is mapped into even the weakest fragment. So yes, good question, yeah. So all of these can be interpreted in the strongest possible way. Right, so what is this going? There are two words here. So totality, we come up with this semantics. What's quite important here is we use a semantics where the fixed points are interpreted as fixed point operators on the candidates, not by their second order codings. And the reason for that is because in order to get this tour to go through, we need to actually formalize the entire semantics inside this theory of arithmetic. So it's a very meta-mathematical approach. And that works crucially because of the semantics we took as fixed point, by interpreting fixed points as fixed points, not as the system F encodings. So this goes through in here, and by a lot of magic, this means that any function representable in here is also representable in here. Something I haven't put here is we actually had to develop a lot of new reverse mathematics for fixed point theorems in order to make this go through. So we had to show that this theory is adequate for proving the fixed point theorems that we need. And then we have a good understanding of, this is a second order theory, and we have a good understanding of its first order part. And this was some heavy lifting done by Michael Mullefeld in the early 2000s in a very beautiful PhD thesis. And finally, to finish the tour, we use a realizability translation. And you can think of this realizability translation as being induced by the realizability translation of second order Heiting arithmetic to Girard system F, but just by restricting to fixed point types. So here we are using the second order codings. So these two purple arrows going up and down, the vertical ones, they actually use two different semantics of the fixed points, which is quite an interesting thing. So I better finish up. So I'm going to skip all of this. Yeah. So yeah, so the main thing I want to say is that this is a question that me and many people were interested in for a long time. And we settled this question. So we showed what was a little bit surprising, that actually circular typing isn't more powerful, at least first order functions, but it was a very complex proof. So we still don't really understand the structure of these things. And in particular, we know exactly what functions they compute, which again was a little bit surprising to some people. They're much more powerful than we thought. I haven't talked about linear logic, which a lot of the authors I mentioned actually talked about, but in fact, these are equivalent. And that's just by proof theoretic translations. In future work, we could think about fragments of mu J, in particular the alternation hierarchy would be quite interesting to study, and also strict positivity, because this is what people use in things like proof assistance. So it would be interesting to understand that, and we suspect that's a lot weaker because it's predicative. And something I didn't talk about was this reverse mathematics of fixed point theorems, and I think there's a good reason to study kind of high order reverse math of these. All right, thank you.
Curious about ULJ and multiplicative additive linearity.
Yeah.
I can see that you can code ULJ into mu A this way.
Yeah.
And is the encoding this way entirely trivial with
good question.
With a double negation translation? Is that...
Exactly. So in fact, it's in gray earlier, so I can just go to it. Yeah, so one way to do it, and this is a lazy way of doing it because you rely on the tour, but you can think of, first this is the one you said was easy, right? So you can use a kind of classical translation here. And now you can do a negative translation, yeah, as you said, yeah. So a negative translation, and then of course, you're losing the granularity of the substructural logic because you still have the same reductions, yeah. Okay.
Okay, thank you very much. Let's thank you for that. The speaker is Omkar. Okay.
Can I ask you to please raise your hand before you ask the question? That question you can write and go ahead.
Plus 2 minutes. I'm going to stop. Yeah, okay, questions.
Your screen is extended. You need to be
Hello all, welcome to presentation on dynamic bidirected dike reachability, or more syllable title would be on the flash static analysis via dynamic bidirected dike reachability. Hello, yeah, so welcome to talk on dynamic bidirected dike reachability. This was a joint work with Krishna, Aniket and Andreas. So I will directly jump to the what's the problem. So problem is dike reachability. We are given a set of alphabets, parenthesis type of k, which is a constant, and k types of parentheses, opening and closing parentheses, and you have one CFL grammar called dike grammar, which is like the parenthesis matching grammar over k alphabets, and we are given a graph with node set V and labeled edge set E, where each label on the edge is from the set sigma. So the task here is to find if two nodes of the graph are reachable via dike path, where the edges on where the labels on the edges will belong to the grammar. Yes. So in this graph, we can see there is a dike path from X to Z, and the path would be X to W, W to Y, and Y to Z, and Z to Z. So this path generates a parenthesis matching grammar which is in S. And this kind of formulation used in many static analysis problems like alias analysis, data dependence analysis, and data flow analysis. So, but our work mainly focus on bidirected version of this problem, where the graph we have, if each edge appears in both direction, if there is an edge on opening parenthesis I from X to Y, we'll have edge from Y to X on closing parenthesis. This kind of formulation also used in many different kind of alias analysis and pointer analysis, and many more other. So why we're doing this is that we try to understand with an example. Say we are given a program, and you want to find whether F and E are aliases of each other, are aliases. To do that, we convert this program into a graph corresponding to digraph. So we may take it later if you have a question how we generated the graph. So here is you can see want to find in the program we generate all the components which are right reachable with each other. Since you can see D, C, E are in a component, so D, C, V, E are aliases. But on the fly means that the programs keep changing since we add lines or delete lines. Yeah, so it's implicit that every age has, for brevity, I'm just showing the complementary ages. You can assume that there is opening age also on that field. So first, so since on the fly, we want to keep the graph changing when we add the lines like one highlighted in green. So this will be the graph when we add that line. This will be the graph when we delete that line line marked the highlighted as 2. So this dynamic bidirectionality can be used in these kind of scenarios. Yeah. So we give an approach where we solve in the dynamic diag reachability when we insert an edge in the graph or delete an edge from the graph. Oh, it's a total new work. Maybe we can take it later. Yeah. Yeah, maybe we can talk it later. It's a big work in itself. Yeah.
You have a set of rules that actually show the translation, or you just have an example?
No, this is just an example to show that how we get a graph. Yeah. So our work mainly focus on working on this graph. So we want to see whether given a graph, we insert an edge and delete an edge, and how we maintain the components with respect to diag components. So this problem was tried in 2018 offline version, but by the Chatterjee et al. In 2018, they proposed an algorithm where they consider the main crux of the algorithm that they take diag SSCs, means the components considering the diag paths as equivalence classes, and they use disjoint set data structure to get a fixed point computation. So let's try to understand with an example. Here again, I'm just showing the closing edges. You can assume that there is opening edge on those complementary, like alpha bar. There is alpha edge from X to U also. So the main crux of their algorithm was that if two nodes U and V are in the same DSCC and they have two outgoing edges on complementary edges on to X and Y, then X and Y will be in the same component. Yeah. So it's diag SCC. So strongly connected components considering the diag paths, which are reachable to each other using the diag path. So diag path is the path where we will get the matching parenthesis. This way. Yeah. So this is a diag path, this path, and it should generate a parenthesis matching. Yeah, so okay. So I'm just showing that X and G are reachable via diag path. So DSCC means that all those nodes which are reachable via this kind of paths. All pair reachability we computing. So you can better understand with this graph. Yes, single component. So here you can see this example. So you can assume that there is opening parentheses also. So here this D, C, E will form one DSCC. Since you can go from D to E, opening parenthesis F on L, and F to C in closing parenthesis L. Again, same from C to F and closing L and opening L bar. And same from E to D. Using this way, you will get the connect DSCCs. Closing parenthesis. Yes. Bidirectional. Okay, so this algorithm, so how they proceed is that since we have two edges from going from same component, here you use a singleton component on same level like alpha bar. So will have X to U on alpha and U to Y alpha. So X and Y will be part of one component. Similarly, because of Z, y and v will be part of a component. And in this way, you get a big component of x, y, and v. Since now x and v are part of component via Dyke path, we'll have path from z to x, x to v, and v to w. Since hence z to w, z and w are also DSCC. So in this way, we get a final DSCC for following the Chatterjee-Ettal algorithm. So they do this as a fixed point computation until we get maximal components. Now you can start from any source. Oh, because there is no edge incoming to you. Yes. Yes. Yeah, but it should be Dyke path. It should be Dyke path, not normal path. Yeah. Okay. So our approach is based on, so this complexity gen square where m is the number of edges in the graph. So we propose algorithm based on, so we first, our approach is we compute the over approximation of affected DSCCs, then we split into singleton components, again like this fixed point computation, and we do the restart the fixed point computation for the affected region. So, but again, to get go to do the fix first, we may suffer n-square complexity. So here we introduce a new notion called primary components, where we split the affected DSCs into these primary components, and after traversing only order n edges, we restart the computation and get able to achieve the so let's see how can we do that. So for the bidirected graph H, we define a primal graph H. So we'll get all the nodes which are Dyke reachable. And then we can say that these are aliases of each other. Yes. Yes, this is means each node is with reachable to each other. Yes. Yes. Yes, they form a, yes. So we split the original graph G, convert to a primal graph H, where each in undirected graph H, we have edges between the nodes. If they are Dyke reachable via Dyke path of length 2, like X and U are, all these are reachable via Dyke path of length 2. So this gives us some primary components. So so the idea of having this is that we can use the techniques from undirected world to have the update. So we remember these components, and rather than splitting to singleton component, we split to this state and restart the computation. But still this approach will not give us n alpha n. So we faithfully maintain the primary components by adding only one edge, while insertion and deleting at most two edges and one primal edge. So let me sensitize how. So this is a graph G. So U and Z are connected, then we add an edge from U to X on alpha bar. Then this will be the new G. So X and Y Z add component. So to represent in primal graph, rather than adding edge from X to V, Y and Z, we'll just add edge to X and Y. This connectivity is still between X, Y, and Z. So we're getting rid of that extra edge from X to Z. Connectivity will still remain same. Yeah. And same for deletion. We will, to maintain the components, we'll just delete the edge from Y to Z and connect X to Y and connect X to G. So to maintain the connectivity in this undirected world. So this is called sparsification technique. Hence with only adding one primal edge in undirected world, we get the primary components and restart the fixed point computation. And same in deletion, with at most two primal edge deleting and adding one primal edge, split the graph into primary components and compute the fixed point with order n edges. So we implemented this approach in C++ and used this testing 22 tool as a black box to maintain the primary components. And we compared with two baselines like offline algorithm discussed earlier and dynamic data log, which is used for incremental analysis. And we evaluated on two set of benchmarks from the data dependence analysis and alias analysis on DCAPO benchmarks. And we divided the benchmarks in three parts, like incremental updates, where we just add edges in the graph, and decremental, we just delete the edges from the graph, and mix, where we add and delete edges from the graph. As you can see, we're way more better than the baseline approaches for data dependence analysis. Similarly, for alias analysis, we have three parts where incremental updates, we just add the edges to the graph, then decremental just keep deleting the edges and mix, add and delete the edges to the graph. Here also, we are better than two baselines. Yeah, that's it. Thank you. So we present in alpha an approach using directed reachability.
Okay, thank you very much.
Hello everyone, I am Divyanjali and I'm going to present my work with Subodh Sharma on dependency-based relay guarantee reasoning. So we'll start understanding the work with we'll start understanding the work with what we generally think about concurrent programs. So generally when we have a concurrent program, for example, here is a program store buffer. Thread 1 is first writing the value x and then reading y into variable a, and thread 2 is first writing y and then reading x into variable b. So when we generally think of the possible behaviors of these programs, we consider all possible interleavings. So in this case, all possible interleavings will lead us to three different results where values of a and b are different and x and y are 1 and 1. This is correct for sequential consistency, but as soon as weak memory models come into picture, there is a possibility that some instruction may be reordered due to pipelining or some compiler or architecture behavior. When that happens, the effective execution will seem as it is coming from a different program. So if in this example, these two instruction reorder, we might perceive an execution where A and B both are 0. So if you are only verifying programs under weak memory model, you are missing out, if you are only verifying programs under sequential consistency, you are missing out on some behavior that may exhibit if we have a weak memory model underlying. And interestingly, most of our machines these days have some kind of weak memory architecture. So those behaviors are happening in the background. We might not be realizing it. Summary is that we have to analyze programs for weak memory model if we want to provide any guarantees. Since this work depends on relay guarantee reasoning, I'll start by introducing classic relay guarantee very briefly. So idea of relay guarantee reasoning is to consider one thread at a time with pre and post condition attached to each instruction, and the execution of other threads are mimicked using guarantees from those threads. So here the instruction x equals to 2 or the thread 2 will have this guarantee that it can change value of variable x from some integer n to 2. And then to get all possible behaviors, we have to consider these guarantees before and after every instruction. So basically that is same as considering all possible interleavings, not reorderings yet. And in that case, our final result will be this here. for thread 1. I am not showing the results for thread 2. So this is classic rely guarantee reasoning. Over the years, a lot of work has been done in using rely guarantee reasoning for weak memory models. So there are most of these works generally introduce some restriction over program invariants or preconditions and post conditions of instructions, which generally make invariant generation more difficult. There is only one, furthermore, those restrictions are specific to one weak memory model. So if you want to go to another weak memory model, you have to change those restrictions. It's not always straightforward. How do you do that? There's only one work so far that tried to parameterize rely guarantee for weak memory models, and that work uses the parameterization in operational semantics, and they require you to convert the operational semantics into labeled transition system. And to do that, you should understand the operational semantic very well, which is again a difficult task for somebody who doesn't know about weak memory model. So in our work, we are trying to propose parameterization based on axiomatic semantics. And our work doesn't require users to understand the semantics, just know what the axioms are. You don't have to understand how exactly the behavior is going to be. Just understand, okay, there is something like this that is there. I'll explain that in the later slides. Second, we propose to use abstract domain to represent precondition or post condition as programs, abstracted program state. So that way we get, we solve the problem of invariant generation, or we make it easier to generate program invariants. Next question we ask is, do we always need to consider all possible interleavings? So for example, if we look at this smaller example and we are only interested in finding the value of R1, then the value of X are not important to us in these program locations. So for example, assertion violation can be one such condition. So to do that, we propose DAP-RG, or dependency based rely guarantee reasoning. The main idea of dependency based rely guarantee reasoning is that if we consider this example, the same example that I had earlier, we will consider instruction D before instruction B only if by considering D, we get a new program state at B with respect to the variables that are defined in B, which is R1 here. So, and C is not going to give us anything new, so we will not consider C before B. The main idea depends on, is based on this dependence relation, where we say that an instruction I is dependent on some instruction J in program state phi. If, so let's say we have initial program state phi, we execute I from phi, we get delta, and we execute J followed by I from phi, we get some other program state delta prime. If the value of variables defined in I is different in both of these states, delta and delta prime, then we say that I is dependent on J in phi. So here is an example, in the same example as the last one. Here, if program state before B is y equals to 0, then B is dependent on D in y equals to 0. But there might be some other program state y equals to 1 where B is not dependent on D. So this dependence relation is specific to program state. B is dependent on D here, sorry, let me see. B is dependent on D in y equals to 0 program state. Yeah, because if you execute B before D, you get R1 equals to 1. The current program stated before B is y equals to 0. So if you don't execute D, you get R1 equals to 0 only. But if you execute D, you get R1 equals to 0 or 1. So that is why B is dependent on D in program state y equals to 0. But if this program state here was y equals to 1, then B is not dependent on D. Yes, yes. You can consider it that if D interleaves before B, then we get a new program state. Y equals to 1 is interfering with B. Exactly, right. Yeah. If B was writing 0, then they will not be dependent. Yes, this dependence relation also has program state, right? So the values are important here. Yes, this is called conditional dependence relation in literature. So further we have interference freedom condition, which these are just some program states. So delta is reached after executing concrete or abstract, anything is okay. If delta prime contains delta, then it will not be dependent. Okay, yeah. So this definition uses a concrete program state. That's right.
So in this example, when you define y as 1,
Yes.
so you are also assuming that R1, the variable of y is live at point B. For example, if let's say there is a statement just before B where you are editing the value of y. So that version of, so this at point D, that definition is killed in that scenario. So
Before B, there is another statement.
yeah, let's just assume that, because
right?
you are here assuming
Right,
that the
right,
value
right.
of y is live at point B.
Right.
So in that scenario, will your analysis, like, will you still consider putting?
So again, it depends on what is the program state right before B. So
Okay.
if this x equals to 1 was also y equals to 1, the program state before B will already be y equals to 1.
Okay.
Right? In that case, we don't get new outcome. So it's not dependent. But if that statement was y equals to 2, we get a new outcome. It is dependent.
Okay, got it. Thanks.
So further we have interference freedom, which simply states that relay of an instruction I must over approximate guarantees of all the instruction J that it depends on in any program state. So for example, here we had B depends on J in y equals to 0. So RB must over approximate guarantees of instruction D. But since B is not dependent on C, guarantees of C may not be over approximated by relay of B. So here we get relay of B as which will say that value of y can be changed to 1. Further, we have a pre-stable or pre-stable condition, which simply says that pre-condition should be insusceptible to changes done by dependent instructions. So in this example, I will not discuss the definition there. I'll simply give you the intuition using this example. So here we have y equals to 0 is ordered below this program state, where y equals to 0 is the state where B is dependent on D. So y equals to 0 is ordered below this one. What that means is in this program state, B is dependent on D. Next, we see that y equals to 0 is also ordered below this one, which means this transition can occur there. So what we can say is, if this transition occurs, y equals to 1 should also be a part of precondition, which is not the case here. Therefore, this is not a correct precondition. But if we change it to y equals to 0 or y equals to 1, then this is a p-stable condition. So yeah, so y equals to 0 is the state where B is dependent on D. Yeah, sure. Okay. Okay, so y equals to 0 is the program state where B is dependent on D, right? If y equals to 0 is subset of precondition, that means in the precondition or the current or the state leading to B is dependent on D, right? Further, if this state is also over approximated by this state, the relay action, the precondition of relay action, that means the relay action can occur here and change the program state to y equals to 1. So what that means is y equals to 1 must also be a part of precondition. Otherwise, we are not looking at all possible states that could come here. Therefore, y equals to 0 here is not satisfying our criteria. So we change it to y equals to 0 or y equals to 1. The criteria is this, that y equals to 1 should be over approximated by precondition in this case. Because y equals to 0 can be transitioned to y equals to 1. Okay, so we have y equals to 0 here. If this relay action occurs here, the program state becomes y equals to 1. So which means the program state, one possible program state here is y equals to 1 as well, not just 0 but 1 as well. So our precondition must over approximate y equals to 1 as well. And that's the condition.
Stable with respect
Yes, that's the stability condition. It has to be stable with respect to this. And to do that, which is not satisfied here, but if we change it to y equals to 0 or y equals to 1, it's satisfied. So the correct precondition in this example should be y equals to 0 or y equals to 1. Is this okay? Should I? That's the classic relay guarantee check as well. These I'm just showing the condition that we change. So that we have to check that precondition. If we transition, so this instruction will have some transfer function. So if we perform transfer function over precondition, we get the post condition. Yes. First, we are checking if precondition satisfies our criteria. Once that is done, then we go to, yes. Then we once that is done, then we go to post condition. Right. So the soundness of DAP-RG simply states that for all instruction in our program, if x equals to v is one possible outcome of instruction I, then x equals to v belongs to post condition of xi, given that x is one of the variables that are defined in instruction I. So let me give you an intuition again with this example. R1 equals to 1 is one outcome of instruction B here. So R1 equals to 1 must belong to the post condition. That's the soundness criteria. And this entire DAP-RG framework is also parameterized in sigma, where sigma is the program state. And the only condition on sigma is that it should be a complete lattice. So we can use any abstract domain as program states there, which leads us to easier invariant generation. And further, so
maybe I'm missing your mark. What are you doing and what are you guaranteeing?
So I am guaranteeing that all possible outcomes of instructions are taken care when all of these conditions are satisfied. So I am sound. I am sound. I'm trying to verify the program under weak memory model.
So you're producing a proof for some assertion.
Yes, I am producing a proof of an assertion.
Assertion is the end of the program.
It can be anywhere.
So you're basically showing that the predicates you get at each point are sound, in the sense that any execution.
So yeah, so basically, if you look at it from assertion point of view, you can simply say if assertion has to violate, then I am giving a violation. There are no false negatives. False positives might be there, but there are no false negatives.
So your predicates that you get over approximating the reachable states at that.
Right. Yes. Yes, yes. We can make it more optimal, but theoretical idea is that. So, okay. So, as I was saying, this sigma is program, sigma that we use to represent program state has to be a complete lattice. Any abstract domain will satisfy this criteria. So, we can use abstract domains to represent the program states. Further, when we try to use DAP-RG for weak memory model, we use the sigma again. So what we do is we designed a abstract domain that is capable of abstracting instruction orderings. And then
what is the weak semantics of it? What do you reorder weaks and rights?
That depends on underlying memory model. This technique is parameterized in weak memory model. Okay, so let's. So let's say you take TSO. So in. Okay, so then we have to see what kind of reorderings are allowed in TSO, and we'll design the program state accordingly. That's the idea. Okay, so yeah. So as I was saying, we designed an abstract domain that is capable of handling instruction orderings, and then use that abstract domain to encode the reorderings of execution as program states. So here we define this domain PO domain or partial domain. Each element of this domain is a partial order. So the lattice is on top of partial order. This is a sample here where A, C is one partial order, and we are kind of making a lattice over these elements. Further, we have defined more over approximations over this lattice. So the over approximation alpha R is again generic and parameterized in relation R that can be defined for a particular weak memory model. What we say is whenever, so let's say here in P1, if A comma C belongs to R, then I will assume whenever C is present in my partial order, A has to be there. So I can delete A entirely from partial order and over approximate it directly to this. Further, this is an example. So I think this will clarify a few things for you. So in this example, this is MP example where if B reads from C and in any memory model where RF is subset of HB, if Y is 1, X has to be 1, right? So in such memory models, when we keep this partial order, B will be ordered after C, which means here in program state, we have X equals to 1. But in a memory model where RF is not subset of HB, B and C are unordered. What that means is X equals to 0 or 1, both are possible here. So that's how we encode the memory model. As an example, we have defined DAPRG for RC11 memory model. And as I was saying, you don't need to understand RC11 for this. What you need to know is what axioms RC11 uses. That's all. So RC11 is defined using execution graph. Execution graphs have multiple axioms as component. We directly map those axioms to partial order without, we don't even know what that axiom intuitively means. We map them one to one, and then we come up with this program state where one partial order per axiom you can take. If you can do something smarter than that, that's good. But if you can't, that is one way of doing it. Further, we have defined relation R for RC11 and transfer functions according to the memory model semantics. We can check the validity of a particular execution by checking the by checking the consistency predicate that are defined by RC11 on any program state. So that is the overall idea. Yeah, it's done. So currently we are in the process of implementing this work in Seahorn, and other future consideration could be construction of relation R. So currently we have defined it knowing what RC11 do, but in general it can be done using some heuristic, counterexample guided, or any kind of approach. Another possibility is the partial order domain that we talked about. It simply keeps track of orderings. They don't have to be program instruction ordering, they can be any ordering. So in any application where orderings are important, this domain can be used. So this is again an example of entire partial order lattice with 3 elements only. If somebody wants to see it, thank you.
So let's see the questions.
So you were not able to.
Let's say there is some precondition there, some post. So let's say these are your two threads.
Right.
And some precondition, some post.
Right.
No, the conditions are across the threads or
So if you're looking at the whole program, it's
across
there. It's across the thread. But when you try to prove, you prove this thread. So you have a condition here and here. This should imply this, and this should imply this.
You have a condition here, you have a condition here, you have a condition.
So this should imply this for correctness, and then these both should imply the final.
Okay, now you want this to be, so you have some condition here for this thread. Let's say.
So there are interleaving that even these states can be implied.
Not needed. After whatever is here, it will be transformed via this instruction to this. Plus, we are looking at all possible interleavings by using rely and guarantee. So we don't need to have the these
Right, so the normal annotation would just say that the normal no logical.
Yeah.
You want this to
For
be
one thread, you simply
from
need
this
to
side
look
to
at
this and come here.
this is
That
full logic.
required
Start
as
as
usual.
code.
But there are some additional conditions because of this concurrence. So for that you have let's say R2 is what this guy is relying about this thread. What would you call that?
Yeah. So what changes this thread does are guarantees of this thread, and those guarantees will be relying for this thread. This is relying that environment can change.
So let me call that rely one.
Right.
Rely
Rely 1 is equal to guarantee of 2, and rely 2 will be equal to guarantee of 1 if there are no more actions.
Okay, so basically this thread will assume that whatever changes this guy makes in one step, okay, are a subset of R1. R1, G2, they're the same thing.
So I can give you an example. Let's say we had y equals to 0. So it can change x to 0. So we can have x equals to n goes to x equals to 0. And it can also change y to 1. So we can have y equals to 1 goes to y equals to 1. These are both guarantees of this thread. Which means this thread has to assume that these actions can happen. Right? And they become guarantee of thread 1. Sorry, rely of thread 1. But if you want to compute all possible reachable program states, then you have to consider.
Whatever one steps moves the
So you don't want false negatives. Therefore, you have to over approximate.
You over approximate whatever possible transition to the other data.
Yeah.
So every state here actually has to consider this.
Yes.
Right. So
Yes,
the
yes.
additional thing apart from the local inductiveness is that this thing should be stable with respect to R1 element. In the sense that if you're here and any transition happens which is within R1, then you should remain within this. Right? Similarly, this should also be stable with respect to anything in there. This should also be stable. Right?
So, for example, if we initially had x equals to, let's say 5, and we know here x can change to 0. So the program state here should be x equals to 0, or x can also be 0.
Okay. Here
From
there is
this
x equal to 1 and x equal to 0 as two instructions.
Yes.
Then we'll add, so it can be, you always have to or x equal to 0, x equal to 1 in each of them.
Right. So in each of these preconditions, not just one. And what I am trying to do is, I am trying to say, for example, let's look at this one. So this instruction, this y is not used here, which means I don't care what are the values of y before this. So you don't need to see this particular guarantee at this point. That's what I'm trying to do. If you don't consider weak memory model anywhere, this is the whole.
Okay, now suppose you have weak. Now
Yeah.
these instructions could be
Reorder. So for that, what we did is instead of just using these, we have that partial order domain, which can capture guarantees. So in that case, if these instructions can reorder, I'll just call them A, B. In our actual execution, A and B will be unordered in partial order component. So from looking at partial order component, we can choose the values. That's clear.
So what is the partial order? The ordering between these two. Right?
Partial order domain is ordering between program instructions, which has to be done according to the memory model. So if memory model allows these to be reordered, then they have to be unordered.
Not every pair of instruction.
Only the instruction, not every pair of instruction is ordered under the memory model. So the ones that are ordered, we consider them A after B. If they were ordered, we will consider this. If they are not ordered, then the partial order will be.
So this ordering is helping you to consider some subset of this relay guarantee.
No. Ordering is helping us in handling weak memory model. If you want it for sequential consistency, you don't need PO domain.
So how is it exactly? How is it ordering to
weak memory model? So in weak memory model, certain instructions can reorder, right? Here we are considering all possible interleavings at all program state, or we are simply considering interleavings, right? But in weak memory model, reorderings happens, as we were just talking about, right? So what happens is, if I don't think that, I will simply assume maybe I should write that empty example that gives nice idea of this. X equals to 1, y equals to 1, it's parallel with read of x, y first, and then read of y. Right? So here, in some memory model, this reads from relation will means that R1 equals 1 implies R2 equals 1, given that x and y are 0 and 3. Right? In other memory models, this is not true. Okay, so what we are doing is, let's say this is A, B, C, D. When this RF happens and we carry the program state from here to here, or we consider the interference from here to here.
Yeah, I request you all to get seated for the next session.
Hello. Is it okay?
Okay, please calm down.
Is it good?
Hello.
Is it good? Yeah.
Okay, it's a bit down there, I guess.
Thank you. Yeah.
Yeah, and you know, go up.
Mihir, shall we get started?
Yeah.
No, I meant to put it a bit higher. Okay, speaker.
Hello. Is it good?
No, I think bring it up further.
Even higher. Okay, is this good?
Yeah.
All right, perfect.
Thanks for coming to this session, and we'll get started.
Yeah. Good morning, and I'm Mihir. I'll be talking about overcoming memory weakness with unified fairness. This is a joint work with Parosh, Fauzi, Advait, and Krishna. We featured in CAV 2023. So yes, this scenario. So here's the perspective we take of concurrency. This is the setup. We look at memory as the medium that facilitates the communication between concurrent threads of the process. So threads can communicate by issuing writes. They can have reads. They can read from the memory, and the compare and swap is something that atomically combines the two. Now, the simplest protocol that achieves this is sequential consistency, where uh, for each variable you have a unique message, you have a unique write that you can use to source your read. But as you'd expect, sequential consistency is slow. It takes a lot to actually implement sequential consistency. And modern processors really care about optimizing for performance. And typically your systems will be distributed. So sequential consistency is not quite feasible. So here's weak memory. So the solution to that is weak memory. And abstractly, when you reason, when you look at it from the perspective of someone who wants to verify programs, there's a whole bunch of messages that you can non-deterministically pick to source as, where your read is coming from. So for W, X, Y, and Z, you can choose to read from some message from an entire set of messages, as opposed to a unique message for sequential consistency. So the weak memory, what we look at is the verification of liveness for programs running under some weak memory model. And the canonical liveness problems here are program verification and repeated control state reachability. And here's the challenge. As far as algorithms are concerned, liveness is a much more non-trivial problem than safety. So if you just take a meaningful fragment of your problem, you're all at sea with respect to algorithms. It's not entirely clear where you begin. And if you try to kind of, tackle this problem, you run into demonic non-determinism. If you make certain assumptions, then the non-determinism conspires in such a way that your problem is rendered trivial. So you really are caught between the devil and the deep sea when it comes to defining a meaningful liveness problem and then actually solving it. So this is what our contribution is. We want to systematically verify liveness for programs running under weak memory models. So there's the devil, there's the deep sea. And what we want to do is first defeat the devil, so to speak, with some notion of fairness, memory fairness that is rooted in practicality, and also something that can be realized, that can be specified through a unified framework. And once we have this unified framework, yes.
What does liveness and fairness mean?
So liveness is basically any property that says something good will happen. For example, we define the notion of termination. So that is, yeah. So termination is a liveness property. Repeated control state reachability is a liveness property.
You include all of those.
So
when you say liveness, you include all of those.
Yeah. So liveness in general is any property that you can't violate with just a finite trace of your run. Liveness is something that you need to observe the entire trace and then you can violate it. And so liveness is basically, it comes from where there is life, there is hope. So any finite fragment of your trace, there is a way to extend it to satisfy the liveness property. And fairness basically means that fairness is essentially a way of excluding undesirable behaviors of your system. So it is an additional condition that your run, in addition to being a run, you need to satisfy a certain property. So it will be clear what these mean. Also from a practical perspective, what these mean, what kind of runs we want to exclude while verifying liveness. So once we develop this framework in which to express our fairness conditions, and we can connect to established techniques, and these will allow us finally to verify our liveness problems. So to particularly answer a question, in theory, well, liveness problems from the Buche automata perspective reduce to repeated state reachability. And so these are the problems we'll consider. Reachability, I mean, not reachability per se, but termination and repeated control state reachability. So again, here's the setup. We saw this while setting the scene, getting perspective. So here's concurrency and weak memory. You have a bunch of threads that execute in parallel, and these exchange messages through the memory that is the shared medium. And so on the top here, you have these little colored boxes. I use them to denote local register contents. And an important technical assumption is that they come from a finite data domain. Here you have an instruction pointer for your program, and together the register and the instruction pointer comprise our control state. And so already we can look at this example here. We can assume sequential consistency still even. So things you expect will happen. So if the most recent write was x equal to 1, you will indeed read x equal to 1. So here in this example, the thread on the left alternates between writing x equal to 1 and x equal to 2. It then reads a flag that the other thread sets. And once it reads a certain flag, it breaks out of the loop. And the second guy sets the flag once he has read x equal to 1. So now, as you can see in the picture, the scheduler might conspire in such a way, it can be so demonically non-deterministic that the guy in the middle is scheduled to read only after, it's always scheduled to read just after x is equal to 2 has been written. So the first guy is sending both the green and the purple messages, but the scheduler works in such a way that just the purple message is read by the other guy. And so this is clearly ridiculous. We need to, so there's nothing in the semantics of a program that prevents this, but we ought to. So that is where fairness comes in. So we have this notion of transition fairness, which basically says if a configuration is visited infinitely often, then every transition, so every successor of that configuration is taken infinitely often. So this is basically strong transition fairness for those of you familiar, but we just call it transition fairness in this talk. So how does transition fairness well fix the problem? So here, imagine you are at a point where the first guy has just written x equal to 1, and the second guy is ready to read. He's literally, the instruction pointer is at the read. And so in our previous demonic run, the scheduler always preferred to pick the right x equal to 2. But under transition fairness, if this situation is encountered infinitely often, at some point he has to pick the guy who will read x equal to 1. And that's it. So you will indeed also read the green message, set the flag, and the first guy can break out of the loop and terminate. So this is how a reasonable fairness assumption is necessary to, think meaningfully about the liveness property of termination. But reality is more complex. As we discussed, the sequential consistency is not how systems are implemented. For example, in one implementation of weak memory is that there can be a buffer sitting in between the threads and the main memory. And if we revisit our definition of transition fairness, it just says if a configuration is visited infinitely often, then something needs to happen. But now here, there are these buffers which in theory are unbounded. So there are infinitely many of these configurations. And so there's nothing that says a configuration will be ever revisited, let alone infinitely often. So transition fairness in this scenario is just vacuously satisfied. So here's an example. Here, the guy on the left just keeps writing x equal to 1 and waits to read x equal to 2. And the guy on the right does the vice versa, keeps writing x equal to 2 and waits to read x equal to 1. And because this buffer is sitting in between, each thread is just confined to reading their own write, which again is ridiculous. You don't see systems. Yeah. Yeah. Is it until or? Yeah, so that's, I think, a flag. I don't quite know, but intuitively, what I want to say is that you wait to read the write of the other guy. So if you,
That doesn't work.
I think it might be buggy, but the message I want to convey is that, well, if the guy sending the green messages is waiting for a purple message, and the guy writing purple messages wants to read a green message, and because this is a buffer, he only ever accesses your own message. What you want to do is flush the buffer so you can actually access the other guy's stuff from the main memory. So informally, what you want is a notion of memory fairness, which, as your question says, as you pointed out, informally, what you want to say is you want to say something like the buffers, quote unquote, because the implementations can differ. The buffers need to be flushed regularly, but this is just too abstract. It's both abstract and informal, as well as too specific at the same time. So to kind of make this more concrete and as well as general, we need to kind of understand what weak memory is, and we revisit the picture we had in the beginning. So you have a bunch of messages you could choose from in order to source your read. So at first you'd think this is completely arbitrary, non-deterministically. But if you study particular implementations, particular weak memory models, one would notice that there is some structure to it. There is some method to the madness of weak memory. And the key observation is this. In a lot of these weak memory models, just consider the writes a thread P makes to a variable X. And you consider the order in which these messages are observed by the other threads in the concurrent system. And so the order of their observation is going to be the same as the order in which these writes were made by the writing process. So what this prompts us to do is organize these messages into channels per process, per variables, and then subsequently the specific semantics of the memory model can impose causal constraints among these messages and dictate what options are available and what are redundant for each thread in the system. So here's a high level relative order of the strength of weak memory models. You may be familiar with some of these, you may not be familiar. The particular details aren't very important for the message I want to deliver in this talk. But for example, some of these memory models are stronger or weaker by design. For example, RMO, PSO, TSO are all part of the same architecture. So for PSO is stronger than RMO because it prevents reads from racing. TSO is stronger than PSO because it prevents writes from being reordered. So RA is stronger than weak release acquire because it imposes a certain total order on all writes to a variable. SRA kind of does away with write races on top of RA. So there is a lot of relations going on, and these are kind of summarized in this slide. So this is a kind of a motivation of the picture we had earlier of why we want to organize things in such a way and enforce dependencies across this data structure. So an important notion here is of configuration size, because we've organized this stuff and then the particular constraints imposed by the memory model will make messages redundant to different processes as the run progresses. So the key is we only need to keep track of messages that are not redundant. And so that's what we do in our data structure whenever we want to model this stuff. So the number of messages stored in a memory configuration is called its size. So that's all that's there to it. And configuration size is an important notion. So we'll just quickly define what a size bounded execution means. So an execution is called size bounded if there exists some number n, such that each configuration is of size at most n. And if this n is specified, of course, we have this very natural definition of n boundedness. So why it is a nice definition is because in actual real systems, you're going to implement all of this on actual hardware, which is physically finite. So you can't have, in practice, you can't have unbounded buffers or anything like that. This actually corresponds to real notions. And this is still abstract enough because you don't want to commit yourself to a particular size. You still want to say, let this limit be there, but arbitrary. And configuration size is a proxy for the extent of weak behavior, because the definition of sequential consistency is this: just one message per variable. So sequential SC configurations have a minimal size. So that's the message here. Configuration size is a proxy of weak behavior. The bigger your size is, the more options you have, the more weak your memory is. And so just setting up the punchline. So configurations with exactly one message per variable are called plain. And the key observation, and this is why SC is so easy to reason about, is that there are just finitely many plain configurations. And an execution is repeatedly plain. And here's if plain configurations occur infinitely often. So now we're getting somewhere to expressing the property, the buffer is flushed infinitely often. What we want to say, and yes.
So there's only one configuration where all the buffers are one.
No, because they can be different, because you also need to take into account what is the actual value that is being stored. Yes, that is also included. No, we assume first that the value is finite. Yeah, the data domain is finite. That's an assumption we made upfront. I think it was also on one of the first slides. So that also is technically important. But it's finite data domain. So you can think of it as the color of the envelope here. So we had green envelopes, purple envelopes, black envelopes here. So there can be multiple plain configurations. Yes? Yes? Yes, if every thread has already read it, or if every thread has read a message that is causally ahead of that message, then there is no way anyone is ever going to read it. So that's why it's redundant. So yeah, so in the bounded thing, what you want to say is that at most these are not redundant yet. So, but the definition of redundance depends on the particular memory model and what causal dependencies it actually chooses to enforce. But this is a general framework. So we have, on top of transition fairness, we have these notions of memory fairness. You have n-bounded transition fairness. You have repeatedly plain transition fairness. And so repeatedly plain is, in some sense, implied by n-bounded transition fair, because if you have n-bounded, then you have only finitely many configurations and you have transition fairness. So these plain configurations that are reachable will definitely be reached repeatedly. So we can also think of probabilistic analogs of this. So what you can do is look at the transition system that your model induces. And it's a graph, basically. If there is a transition from here to there, you have an edge from here to there, you have some non-zero probability from here to there. And if the probabilities are aligned in such a way that the set of plain configurations are visited infinitely often with probability 1, then this is our definition of probabilistically memory fairness. So so you don't enforce it, you just load the dice in such a way that the probabilities ensure this condition for you, this favorable buffer flushing condition for you. And such Markov chains are nice. We have a name for it, they're called decisive. And what the set of plain configurations is a finite attractor, means they're visited infinitely often with probability 1, and it's a finite set. And why these are nice is because for decisive Markov chains, if you take any set F, there is a dichotomy. Either this set will be eventually visited with probability 1, either the set is eventually visited, or you'll get to a point where you can no longer visit this set. So that is why they're so nice to verify. And there's the shape from the earlier slide, because decisive Markov chains are well studied. At least for our purposes, they give us exactly what we want. So when we ask this liveness question, does the program terminate? Is a control state reached infinitely often? These are liveness queries, and for a fairness assumption, there are these three fairness assumptions: probabilistic, n-bounded, repeatedly plain. And regardless of which of these three you choose, your decision for the liveness query is going to be the same. So all of these three are kind of equivalent the way we've set this up. And that's a punchline. And to prove this, what we will do is associate with each of these problems a canonical object, which is a graph that looks like this. So I'm only going to sketch the proof here. So this is a graph. The vertices, so this is a parameterized graph, so G of n. And the vertices are the plane configurations. And so what are the edges? So we draw an edge from gamma to gamma prime if gamma prime is reachable from gamma via configurations of size at most n. And what are these colors then? We paint a node green if the control state of interest, for example, the terminal label or the thing you want to visit infinitely often, is also reachable from that particular plane configuration. So if you can reach, if you can do stuff you're interested in with via configurations of size at most n, you put an edge or you color the graph and so on. And so you get this sequence of graphs. Yeah, you get G1, G2, and Gn and so on. And the key observation here is that this graph is finite. This underlying structure is finite. So you can only add edges, and the nodes can only go from black to green, because this is a reachability graph. It has a finite widthness. And so this thing is going to saturate. It's going to saturate, and it's going to be the same for sufficiently large n. So let's call it G. And this G right here is the canonical object for repeatedly plane things, probabilistic things, and n-bounded things for sufficiently large n. And so all that remains to be done is, well, liveness holds if all bottom SECs are colored green. So because of this fairness, you know that you're going to get to a plane configuration infinitely often with probability 1, if that's relevant. And because of fairness, you know that if you're there infinitely often, the stuff that you're interested in is also going to happen infinitely often, because it has this finite path to happen. So yeah, that's pretty much it. So the only remaining step to actually verify liveness is actually construct this graph, and that one can do with reachability queries. So in this particular setting, we've reduced liveness to actually a safety property. And yeah, so we just need to do a little bit of a translation. It's cumbersome. You need to look at a particular memory model to do this. But if you can do this, you've essentially reduced liveness in this scenario to safety. And revisiting the chart of models we had, the models in blue font are those for which the underlying safety problem is decidable. For the purple ones is undecidable. So already directly we have, in theory, that liveness for these models is decidable. Yeah. And that's it. That's the last slide I have. So that's the framework, and this is the talk. Thank you.
So we have time for a couple of questions.
Yeah, there's a question there. Okay. No.
Okay. Yeah, so I'm curious.
Oh no.
Hello. Hello, Mihir.
You are borrowing my connector.
I don't. Yeah, I need.
Yeah. Okay. Fine. Yes.
Yeah. So you did it for SRA and WRA. So why not for RA?
Because RA is like undecidable. The underlying reachability problem is undecidable. Okay. So if you have some framework that approximates answers, you can, call to this framework, construct the reachability graph, and do it. And so, okay. Yeah. And there's a question there as well.
So
Just curious about the general setting. So I mean, I was a little confused by the graph, which two identical graphs, one in which you had green nodes and one in which you had green and black nodes, and they looked identical to me. So I was just curious of what was happening here.
So that was rather unfortunate notation.
Okay.
So the black node, so you color a node green if the node can go to somewhere you are interested in.
Now, how would you classify this whole approach? With this, do you see this as an abstraction of an operational approach?
Yes.
I'm curious then about your very last assertion that, oh, you've reduced the liveness property to safety, but then this is under some finiteness assumptions, right?
Yeah, this is under this particular fairness assumption.
Do you have a corresponding notion in terms of, I understand safety properties as closed sets and liveness properties as dense sets.
Yes.
So do you have a corresponding way of characterizing what you're doing in terms of closed sets and dense sets in a topological order?
We haven't thought of a topological.
Think about it in semantically.
In this particular context, no, we haven't thought of a topological thing. But thanks for the. Yeah, thank you.
Hello. 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 I'm audible, right? Fine. Yeah. Hello, everyone. I'm Madhukar Yeragundla, and I'll be presenting my joint work with Sanjeeva Prasad and Subodh Sharma on security preserving verified compilation of synchronous reactive data flow language. This work is currently under submission to ESOP. All right. So Lustre is the synchronous reactive data flow language in the title. It has deterministic and declarative semantics, and it's currently used to model systolic algorithms, critical control systems, and digital circuits. Valus is a compiler toolchain for Lustre written in Coq, and it's built on top of ComSet. So the translation is verified end-to-end from Lustre to the assembly language. And the objective of our work is to add secure information flow analysis to this compiler toolchain. So yeah, in Lustre, you model devices as transducers of clocked data streams. These devices consume and emit sequences of values on event-driven clock, hence the reactive nature. So what you see here on the left is the controller node in Lustre, which takes in temperature and the user presence as true streams of input and returns a stream that turns on the air conditioning. And the equation for AC on essentially says that if the temperature is above a certain limit and the user is present, turn on the air conditioner, otherwise turn it off. And every Lustre program can be represented as a network block diagram. And what you see here is its representation. Yeah. So Lustre programs are made up of expressions, each of which generate streams, like the if highlighted here. They are also made of, yeah.
Parameters both come together.
Yeah. I mean, I have an example run of the program, so probably, yeah, you're right. They come synchronously. The equations are unique in the language, meaning that within the body of the node, you cannot redeclare or redefine AC on again. And the order of the equations doesn't matter, this affect the semantics of the program itself. And finally, Lustre programs are made up of nodes, and which are essentially abstractions that take input streams and convert them into output streams. For a program to be well formed, nodes should not have recursive calls, meaning the controller node cannot call itself within its body. There are also no global variables in Lustre. It's only input, output, and local variables. So this is an example run of the program. As you can see, AC on is defined only when both temperature and user are defined and not present otherwise. Lustre compiler also has a series of clock consistency checks that make sure that the temperature and user are defined exactly on the same clock syntactically. Let's quickly convince ourselves that, yeah. Yeah. Yeah, so there is no value. It's just that the clock tick, the program ticked, but because temp and user are not defined on that clock, they are defined only on the odd pulses of the.
Only one of them is different.
Yeah, so that's an invalid program. Lustre compiler actually filters out such programs. It's not a well-formed program. There are a series of clock consistency checks that make sure that syntactically both temp and user are defined on the same clock. And which again in turn define the flow, the clock for AC on itself.
That's a runtime property, not a syntactic.
No, there is a way to ensure it syntactically as well. I mean, it's a well-studied piece of work. For example, if you have two clocks which say x greater than y and y less than x, if you have two streams, these two streams are not considered equivalent as clocks. So in fact, if you cannot perform an operation together on such streams. Does that make sense? Maybe we can take it up later. Yeah. So let's quickly convince ourselves that you can still write insecure, quote unquote, insecure programs in Lustre. So if the user was a secure input, secure stream, user presence, and AC on is publicly broadcasted, you are essentially on a hot summer day, you're broadcasting to everyone that user is not present at their home. So this is the Wales verified compiler toolchain. It goes through a series of phases and including the COMSAT phase, starts at Lustre and ends at assembly. Yeah, and also goes through a series of data flow semantics. So every translation to each and every phase is verified to be semantics preserving. In today's talk, I'll only focus on the top three. And in this, we are going to add analysis to the secure information flow analysis to each of these phases, with the idea of saying that we essentially want to say, is the Lustre program secure? Is the N-Lustre phase secure? And so on and so forth, so that we can verify that the translation is also preserving the security properties through via these analysis. So what's the intuition behind adding a secure information flow to any of these phases? So it's like what Sanjeeva pointed out yesterday. Given a security lattice in the style of Denning, we tag the streams with privilege levels, account for explicit and implicit dependencies, and ensure that the assignments and the equations that follow in each of these phases uphold the security levels assigned to each of the streams. Yeah, but how do we verify and what constitutes security? And as Sanjeev has already said in the talk yesterday, it's via the notion of non-interference. It's a semantic notion of security. Consider we partition the program into two halves on a security level, where all the streams below a set level, say public, are ordered below, and the other partition is just either above public or unrelated, and we call it secret. So if you change the inputs on the secret streams, keeping the inputs on the public stream the same, the output should not show a difference for the program to be non-interfering. If they change, essentially that means that there is a security, there is an information leak from the other partition into the public partition. And this property, as you can see, it's a hybrid property and it's a hard property to verify. Yeah. And the approach we want to take is instead of verifying, we want to infer the security at the compile time, just like the clock calculus. And we do so via a type system for adapting the approach of Valpano. The type system encodes minimal requirements of secure information flow. And for expressions, it essentially says that the security level of the expression should be at least as high as that of its components. I'll come to the type assignment parts later on as well. For equations, it says that the defined variables, the security level of the defined variables should be at least as high as that of the RHS expression. And finally, at the node level, and the system level, we generate signatures which say that input streams of level alpha are converted into output streams of level beta, provided the constraints rho are satisfied. The gamma stands for the input clock security level, and kappa is the reset level of the reset security level. I'll come to the reset part when I explain the semantics of reset, which towards the later part of the talk. Yeah, so the security, I mean, okay, I guess I should have I preempted a little bit. I'll come to that part again. So as you can observe, there are no local variables in the signature themselves because they are soundly eliminated. This constraint eliminate the local variable elimination from the constraints is proven to be sound in Coq. And what we do is when there is a call instance or a node instance, we substitute the input argument security types to generate the new constraints for that particular node instance. And the types are symbolic, which is why I'll come to your point. So we assign a fresh type to each of the streams, whether inputs or outputs. And when the constraints on equations essentially say that, look, the security type that is assigned to the defined variable should be at least as high as that of the the expression on the right. So I'll give you an example in the next slide. Now, this is the grammar of the types themselves. Bot here represents the bottom in the security lattice. It's always tied to that part. The types are symbolic. So symbolic types along with the constraints essentially means we are a type inference system, not just a type checking system. And the part item highlighted in red is a qualified type. It says that a stream has a level alpha provided the constraints rho are satisfied. And this appears only at the Luster level, and that's why it's marked in red. NLuster, STC, and the other imperative phases do not use this type at all. So here's the intuition behind the rules of what the type system does. When you have an expression, this is a sampling expression. When you have an expression that says E when X is true, so it samples the value of E whenever X is high, and E has the security type delta and X has the security type alpha. The combined expression has the security type of alpha and delta. It needs to have the permissions of both of these. The rule on the right essentially says the same thing, but gives it for a tuple of expressions. For equations, the type rule says that it generates a constraint. Yeah.
What does the join symbol mean?
It's a lattice LUB operation. It's a symbolic lub. It means that the permissions of both alpha and delta.
Where is the lattice here?
Okay. Yeah. This in a very simple setting, this would be the lattice. You have a secure private information and the public information, which are ordered this way. And the lub of secure and public is public. Sorry, secure.
And what do those symbols mean? The type symbols those symbols represent points in the lattice.
They are mapped to it. You can it's the entire analysis is parametric in the lattice. So you can plug in your own lattice mapping to each of these variables.
Each symbol represents a lattice point.
Yes, yes. Each symbol represents a lattice point, and these variables in the these variables in the types. These are essentially variables. You provide a mapping as a user saying, I want this type to be at least as the input type of this stream is as high as secret, and the other one is public. And the rest of the types are inferred from the constraints, which is why we are a type inference system. For equations, once you have the expression, which is assigned on a clock CK to the output variable Y, the constraint says that beta should be at least as high as all the components of the expression, including the assigning clock. And that's what the constraint here, the type rule here says as well. This generates a constraint, whereas this assigns a type. That's the difference between the syntactic levels. And what we have from the type system is a bunch of constraints once you finish the analysis. And we call a program as well-typed when every call instance is well-typed. And given a type variable to the security lattice mapping, all the constraints that are formed are satisfied. Now, the core theorem we have is that when the system, the analysis says that it's well security typed, the programs exhibit non-interference. So this is the main theorem. And we proved this for NLuster's, we proved NLuster's non-interference in the 2020 work. And we would like to have a similar result for Luster. Turns out it comes for free and very nicely comes out, which is what I'm going to show here. So if you have a Luster node F, and the analysis says this is my node with constraints rho, and normalization converts it into n-Luster node of type this with constraints rho prime. Notice that the symbolic type variables are one and the same, except the constraint could be different or readded in a different way. The main result is that the satisfiability of rho implies satisfiability of rho prime. So what you have is type preservation. So now chaining this with, we already have a non-interference for n-Luster. Chaining this with the semantics preservation of Luster, the normalization pass, along with the type preservation, you have non-interference for Luster for free. And this is a very simple theorem in Coq. We would like to have something similar for the STC phase as well, but turns out it's slightly more complicated than the Luster phase. Before that, I need to explain to you why the Whalers team felt a need for this STC phase itself. So that comes from the operator called reset. Reset is an imperative operator that's recently introduced in their 2020 work. It's an imperative operator and causes implicit information flow. So what we have here is a countdown node that takes an initial value and counts it down all the time. So it goes on infinitely, keeps on decrementing the value. And what we have is an instance of this countdown node with the reset stream edge. So whenever edge is true, this particular node instance is reset to its initial state. So the countdown, the timer goes back to 5 whenever the edge is true. Now, this is too drastic a change to prove the translation correctly to imperative phase, which is why the Whalers team built in an intermediate phase for to easily gradually reduce the semantics. So into the next STC phase that I'm going to talk about has transition system semantics, which provides slightly more granularity for the translation proof to go through. So this is the translation of the program from Luster to STC. I skipped the n-Luster phase. What's happening here is that let's first look at the countdown node itself. You have the node becomes a system here with 2 transitions. One is an init transition and the default step transition. Whenever and the reset call itself is split into 2 parts again, the node instance and the reset statement for reset. So whenever edge is true, it triggers this init transition, resetting the system back to its original state, the initial state, and otherwise the step transition keeps on going. So by composing the effects of these 2 transitions, you get the same effect as that of the original Luster program. Now, what the difficulty this poses is these memory variables are introduced only in STC. They are not present at the Luster phase. And these allow for new ways to interact with the program itself. And again, so we need to prove that for non-interference that nothing fishy is going on here. And these are not a new attack surface than the original program was. So there's the non-triviality in the non-interference proof. And the other one is the dependence on edge is further broken down in the STC phase because there is no straight up. So yeah, the dependency is broken temporarily. What we do is we maintain a context for these reset types. So whenever this statement is encountered, I generate a constraint on the reset type of edge and plug it back into this instance. So that's where the kappa in the node signature comes from. So this is how we deal with the complexity with the reset in the STC phase. Yeah, and the future work is currently in progress. I'm encoding the proofs of these non-interference in Coq and integrating it into the Whalers toolchain. The next obvious work is to extend it to the final the OBC phase, and it turns out the same constraint-based approach that I've shown until now works even at the OBC phase. This is not how it's usually done at the OBC. I mean, the imperative phases. It's generally only the type checking, but we are also doing type inference there. And finally, as I earlier indicated, it turns out while developing this, we figured out that the clock calculus is doing something similar to what we were doing while developing the dependency calculus for the secure information flow. So we believe that there is a core calculus of dependency that's common, that can commonly encode all these program passes. And there is a precedent for this in this work, Abadi et al., where they do it for program slicing, secure information flow, call tracking, and partial evaluation in the popular 1999 work, and that's for an imperative language. Finally, a similar type system for VHDL and Verilog, which are also data flow languages, has decent applications there where you can discover security policies for, like, let's say if I have a register, should it be accessible to the software bus or not? You can figure out such kinds of policies using a similar flow developed for these languages. So that is all, and let me know if you have any questions.
Yep.
Just wanted to ask, you said that the system was this type system was minimal. Can you just expand on?
Can you?
You said that this type system, these rules were minimal. Can you just say in what sense you
Type
meant?
system is used in minimal. Yeah. Okay. So the constraints that are generated are guaranteed to be that they don't over constrain the. I mean, they allow all they can allow, and they do not constrain it more than needed. That's a. But it's only syntactic minimality, not semantic minimality. Meaning, if you have a program, okay, I can discuss the example with you later on. But yeah.
So I mean, I think the analogy you should have seen functional languages like OCaml or standard ML. That's the notion of a principal type. So this is sort of a disaggregated version of the constraints that you get are absolutely minimal constraints, and anything that solves these constraints will be, it's got no more constraints than need to be.
Yeah. The type that you get as the solution for these constraints is the most general type that's possible.
So did you do that? Maybe I missed that. Did you do did you also verify the translation?
I didn't do the translation verification. That's done by the Wales team.
I mean the fact. I mean, if the original source is, I mean, let's say it is secure,
right?
Based on your lattice and your mapping for various.
Right.
Have you also checked that the transition system translation also satisfies that?
Yeah. So that turns out very nicely in the framework. So once you have these similar looking analysis on each of these phases, to say that the security properties are satisfied essentially boils down to saying that if my constraints at phase 1 are satisfied, then I just need to imply that the constraints in the second phase are the satisfiability of the second phase are implied by the satisfiability of the first phase. So that's how I make sure that the security policies the properties are translated throughout the framework.
Okay, so you verified that this translation kind of propagates preserves the.
Yeah. Right. So these type annotations are carried within the translation, and once the translation finishes on the body of the program, I verify that the type signature that comes out from the enlisted phase and the listed phase are quote unquote equal or equisatisfiable is the right term, I guess.
So you don't have any pockets?
No.
Okay, in that
Over
case,
here.
Yeah, you click on.
Yeah. And this way you need to hold. Yeah. Hello.
Yeah, but you're deliberately pointing out this. Talk regular.
Okay. Okay. Good afternoon. So is it?
We need to build up.
Okay, fine, right?
No, I meant the clip a bit.
Fine.
Should be now. Try speaking.
Okay. Okay, I'm going to present my ongoing work related to the verification of a garbage collector for OCaml. So it's like a proof by construction verified garbage collector for OCaml. So it's a joint work with Dr. Karthik Nagar and Dr. K.C. Shivaramakrishnan. Those are my guides. And I have two technical collaborators who are Dr. Karthikeyan Bhargavan from India, Paris, and Deepesh Kafle. He's a student at NIT Trichy. So, like, what is a garbage collector? So, a garbage, like, we all very well know that a heap memory management can be divided into two. Like, it can be either done manually or it can be done automatically. Okay, so manual memory management is like programmer control, whereas automatic memory management is system control. So manual memory management, we know that we use this free malloc, those kind of things to manually allocate memory and free memory. Whereas in a garbage collector, it's automatic. So a garbage collector is used, which is functionally equivalent to free, and an allocator is used to allocate memory. So like the languages which uses manual memory management are C, C++, and the languages which uses heap memory, automatic memory management are OCaml Java. So like well-known algorithms like mark and sweep, copying collection are used for garbage, used as garbage collection algorithms. Manual memory management is error prone. It can cause memory safety bugs. Whereas automatic memory management can be made free of this, one second. Okay, free of memory management bugs if it is formally verified. So like why GC is important is as I said, this is statistics related to usual memory management bugs. Like in blockchain projects, these are showing that since it is written in C language, there are a lot of memory related bugs like memory leaks, dangling pointers, those kinds of things are happening, which are actually causes a lot of memory management issues. So it can cause crashes and it can cause a lot of billion-dollar losses also. So it's very critical that memory management should be handled correctly. So this is our problem statement. A verified and efficient. So we stress the point that verified and efficient. We should not lose the efficiency in the sake of verification. A verified and efficient garbage collector for OCaml. OCaml is a general purpose industrial strength language. Okay, for the correctness of the GC, there should be two properties it should satisfy. One is GC safety. So GC safety says that GC should free dead allocated objects only, that is unreachable from program variables. GC safety actually implies memory safety, and GC liveness, which says that GC should free all dead allocated objects. So, but GC verification is not something new, age-old technique actually. So, what we have done differently? So, this is a analysis of where our work stands in the case of GC verification in literature. There are broadly pen and paper proofs as well as mechanized verification. Our work goes in the category of mechanized verification. Okay, our work goes in the category of mechanized verification. So it's fully automated. Under mechanized verification itself, there are two categories: mark and sweep GC and copying collectors. And we are doing a mark and sweep GC. And actually, our work is this. So, like compared to it's like we are taking a middle way between abstract models of practical GC and a real practical GC. So, like the differentiating factor from the real practical GC is that the real practical GC, which is written by Pretrang, is tied up with x86 assembly, whereas our work can generate or compile to executable C code. Okay, this can be actually integrated with the OCaml runtime. So it's like a proof by construction approach of generating the C code. And one more thing is that this practical GC is actually tied up with the GC algorithm specific, whereas our work is tied up with the abstract graph specification of reachability. So I will explain those kind of things. So this is where our work stands. Okay, so now garbage collection, we can model it as a graph problem. So it is like given a heap H. So a heap memory we are considering as a linear heap. Given a heap memory H, the graph G of H equal to VE, where V equal to set of allocated objects in the heap and E equal to set of in all interconnections between allocated objects. Now, one more definition we need to know is that reachable subgraph. So this new definition we are creating, that is reachable subgraph is RGHR. So it is input by a heap, and where R is the root set. Like root set is nothing but the program variables. The program variables through which the heap memory is accessible. So reachable subgraph RG of HR equal to VRG ERG, where VRG is a set of all reachable allocated objects from the root set R, and ERG is a set of all interconnections between the reachable allocated objects. So these definitions we are following for our specification. Now, so as a running example, this is a graph and reachable subgraph. So if we can see that the graph is the graph is formed out of all the, so this is like if we take the ID of the allocated objects A, B, C, D, E, F, those are allocated objects. There is a stack which is used for keeping the root objects and like just keeping the running the algorithm. So allocated objects are A, B, C, D, E, F. G of H is actually formed out of the allocated objects, and if you see that reachable subgraph does not have E and F, because E and F are not reachable from the root set. So it's a running example. Now I want to quickly explain what is a tricolor Mark-and-Sieve GC. So a tricolor Mark-and-Sieve GC is like, as the diagram shows, there are three stages: before mark, after mark, and after sieve. So it's like all the allocated objects will be like white. Like if we can put a color, it will be white. And while the GC proceeds, actually the stack will be containing the roots, and like the roots which the objects which are directly pointed by the root will be colored gray, and no objects will be black before the GC. While how the mark proceeds is that one by one it will run in a while loop infinitely for a while loop until the stack is empty. It will pop out one by one each object and color it black and push all its pointers back to the stack. This procedure will continue until the stack is empty. And when the mark finishes its execution, what happens is that all the black objects will be actually the all reachable objects, and those which remains as white are unreachable objects. Now, when sweep comes into picture, what sweep does is that sweep will scan the heap from the low address to the high address and picks up one by one, examines one by one objects. If its color is black, it will be converted to white to make it ready for the next GC cycle. And if it is white, it will be actually added to the free list to make it available for the next allocation. So this is a typical Mark-and-Sieve GC. Now we can see that
sequentially scan.
Sweep will sequentially scan. Yes. So we can see that. So when I explain this algorithm, we can inherently feel that this is nothing but a depth first search. This is a depth first search on the graph, like graph which we created as earlier, as I said, we're starting from each of the roots. So it's inherently a DFS. Now, we need to observe that the mark implementation does not construct any graph. So this graph is constructed for the explanation purpose that when we do the verification, we need to actually construct a graph. Implementation does not construct any graph, and there is no incur of efficiency or no causing limitation of efficiency due to mark implementation. Now, I'm going to specify the GC correctness, which is independent of the mark algorithm, and it is purely based on the graphs. So it is like this. So before the GC, we will say an initial heap H0, such that it is called a well-formed heap. It is called omega of H0, which says that all allocated objects should point to allocated objects only. So this is an invariant condition which is needed for the GC. And this is if this condition is not satisfied before GC, it's not guaranteed that it is satisfied after the GC also. So it's a precondition. Sorry, it's a post condition which should be given by the allocator. Now the first statement says that the post conditions of the GC states that after the GC finishes, a new heap is formed, which is H1. What it says is that all allocated objects still points to allocated objects. So that is why it is omega of H1. What it says is that memory access are to allocated blocks only. So GC does not incur any alteration to this property. That means the memory access are still to allocated blocks only, and that is actually needed for memory safety. Now, the second property says that the new graph G of H1 is equal to RG of H1. So if you construct a graph and if you construct a reachable subgraph, those should be exactly the same on the new heap. This is to say that all garbage is gone, because in the allocated objects, like as I said earlier, the graph is constructed with the allocated objects only. So when they become equal, all the garbage after the sweep phase, they are actually added to the free list. So all garbage is gone. So it is actually for liveness. And the third condition says that, so it's also a very important condition. It says that if you have a reachable subgraph in the initial heap H0 with the same root set, the final heap also should have the same reachable subgraph with the same root set. So that's what this property says. So this is saying that the reachable subgraph of the initial heap is the same as the reachable subgraph of the final heap. That means during the process, we have not lost any of the reachable objects which are initially reached by the root set. So
isn't this third thing enough? Just the third property?
Yeah, okay. So the first property, through the first property, actually we are deriving the third property.
Doesn't necessarily imply the second.
Yeah, second is yes.
No, you have the reachable subgraph.
So if the reachable subgraph might be the same, but in H1 it still might have garbage, right?
Yeah.
No. Okay, no, sorry. I meant the actual graph should be the same as the reachable subgraph.
Yes,
That
yes.
should be your property.
Yes, yes.
That's only one property.
You mean to say the second property? No, right?
No, so the third one is the reachable subgraph of the initial heap.
Yes.
Is the same as the graph of the final heap.
Reachable subgraph in the initial, no, reachable subgraph in the final heap is same as the graph in the final heap. That is the second property.
Yeah, and that should be the same as the reachable subgraph of the initial heap.
Yes, reachable subgraph of the initial heap. Yes, exactly.
This we are saying that there shouldn't be any spurious.
Yeah.
But if you just said that the final graph
yes
is equal to the reachable subgraph of the initial heap.
Yes, that's by transitivity.
That is, yeah.
I mean, just that property seems to be enough.
Yeah, in order to, yeah.
It also implies that there cannot be any spurious unreachable.
So that's broken into these two. So that's it.
Like we can nicely capture those liveness and safety if we break down. Yeah. Yeah, okay. So 2 and 3 actually implies the reachable subgraph is preserved and all the garbage is gone. Yeah.
That's your question.
Okay. So in order to, like, I'm telling about a GC for OCaml, right? So in order to understand the GC for OCaml, like the GC for OCaml should handle an OCaml style object. So we should understand how an OCaml style object will be. So a typical OCaml style object will be like this. It will be having a header, and a variable number of data fields. So it will be like this. Field values, the variable number of field values are value 0, value 1, those kind of thing. So field values can be either an object pointer or an immediate integer. Like how we determine like that is based on the value. If the last bit is 1, it is an integer. If it is 0, it's a pointer, object pointer. So then like this one object size. So the header value. So the header value actually like bitwise manipulation is done to store different 3 different things into the header value. So the first, depending upon the machine, if it's a 64-bit machine or a 32-bit machine, it depending on that 22 or 54 bits will be allocated for number of fields which follows the header. That is called object size. The next 2 bits defines the color, and the last 8 bits defines the tag. So tag is nothing but it defines the type of the object. So some objects will be no scan object. GC should not scan the fields of such object. Some objects will be closure objects, infix objects like interior pointer objects. So those kind of things. So tag defines the type of the object. And so for the construction of the object graph, the successors of that object is like its field pointed. So as I said, there can be integers as well. During the graph construction, the integer should be omitted and only the field pointer should be taken into consideration for the for constructing the successors of the object. So in OCaml, there is a convention that the ID of an object is its first field address. So this is a basic thing which we need to know about OCaml. Now the question is that we can't directly use naive DFS because of efficiency reason. Because as I said earlier, our aim is not only verification but also to construct a GC which is efficient. So why naive DFS cannot be used? DFS uses a visitor set and a stack because in order to avoid cycles, So DFS does membership checks on visitor set and stack to avoid cycles. So this is actually not efficient because of this membership check, because in the worst case it can go to till the end of the stack, till the end of the visitor set, like those things. Now mark. So we need to so what we have to do is that we need to encode the DFS functionality into mark. At the same time, we need to avoid the membership check. So what we have to do is that we can just make use of the OCaml style objects facility. There is a facility of color. So we have seen that there are 2 bits are used to represent the color. So what we are doing is that we encode the membership as colors. So gray color means it is in stack. Actually 2 bits can represent 4 colors. So gray color can represent it is in the stack. Black can represent it is in the visitor set, and white can represent it is unvisited. And there is one more color, blue, which I haven't told. Blue is like free object, like it's actually part of the free list. Now it is efficient because only 2 bits check is required. Now I am just showing a feel of the verified extracted C code. We don't need to understand how the code and all, but we need to just see how the code looks like. So this will be the extracted C code. So what we need to see is that there is something called make header. So make header function. So there is something called make header. So make header function actually, like all the bitwise arithmetic is done by this make header function. So it is like color. What color header does is that since membership is not is avoided, right? We are actually maintaining that information by coloring the object. So all the bitwise arithmetic calculation comes in the color head function. And now this is like the mark C code. So if we see here the mark, so the mark code actually it is actually encoding the graph reachability actually. So if the mark is running on a while loop until it is able to find all the reachable objects, so it's encoding the graph reachability. And finally the sweep function, so it is like it's a subgraph preserving. So sweep also should maintain the coloring property should ensure that the sweep correctly adds only the free blocks or unreachable blocks to the free list. So that is actually, so together mark and sweep together preserving the subgraph property. Now memories. One more thing we need to be aware that why I have shown this code is that I have explained what is graph reachability, like inherent graph reachability which is happening. On top of that, there is a bitwise arithmetic happening. And now we need to know that this is a C code. Okay, so this C code is extracted. So before extracting, this C code is verified such that it is not violating any memory safety properties of the implementation itself. Like we are not it's like no buffer of overflow is happening. No allocation is happening to a like non-allocated buffer. Those kind of things are ensured before extracting this code as C. So the challenges in verifications are 3. As I said earlier, this is a graph reachability problem. It's a depth first search over a graph with cycles. So it can naturally form a layer 1. So we need to independently verify the graph, the depth first search reachability property itself. It should be a strongly reachable thing. Now, second concern is that mark uses bitwise arithmetic for efficiency. So naturally it forms a layer 2. And the third one is that this implementation is in C. So as I said earlier, C implementation's memory safety issues also need to be verified. That forms the layer 3. So that's the concrete implementation. So it's like an intermingling of graph reachability with bitwise arithmetic over a C implementation. So this is the complexity of this verification. So separation of concerns is required for handling the verification. That's why we separate into 3 layers, which is like a refinement approach, as well as we can reuse the correctness specification. Also, we can see that the first layer is like a very abstract layer. It's defined over a very general graph with cycles and a verified depth first search, which can be independently used for other applications, not only garbage collector. That's why we separated like this. So this is our overall approach. So as we can see, so this is the tool we have used is F-star Lowstar. So F-star is a proof-oriented, solver-aided programming language, and Lowstar provides facility to write C-like code with memory safety verification, like no buffer overflow, and it can only use live buffers, etc. Those kind of things are enforced. So this is our layer. So the topmost is the most abstract layer, graph DFS, where we are proving that the DFS is able to put all the reachable and only the reachable objects in the visited set. And the second layer is a functional mark and zip GC, and the third layer is an imperative mark and zip GC. Functional in the sense that it is working on unbounded buffers, and imperative in the sense that it's more like concrete. It is working on fixed length buffers, as well as it is using iteration instead of recursion. So so this when we write something in Lowstar, we can, using a caramel compiler, we can extract the C code out of that. So the DFS input will be a graph G, a stack ST, and an empty visitor set, and DFS output say visitor set, which contains all the reachable and only the reachable objects. So that is important. And functional mark takes a linear heap and a stack, and output say new heap. That's a functional heap. And the third layer is effectful program. So it is doing mutation in place. So we don't have any, like in place, it is doing the update on the buffer. So these are our backbone theorems for doing this proof. So the first theorem is that the DFS, if we run on a graph and a stack and an empty visited set, what it has to produce is that like the output of the DFS should contain all the reachable and only the reachable objects from a root set. That's the first theorem. And the second theorem says that when we do the mark on a heap and on a stack, all the black objects in the mark, should be such that it is equivalent to all the yes, I'm winding up, sir. It is equivalent to if you run a DFS on a graph constructed from the linear heap, that is G of H, with the same stack as input and an empty visited set. So it is like this. This DFS and this DFS are same. So this is the equivalence we are proving. And then the concrete layer, which says that if you run the f of H1 is like the I think it's not working. Okay, f of H1 is like the functional equivalent of the concrete heap in memory M1. That's the final memory. It's equal to if you run a recursive or functional mark on the functional counterparts of these initial heap and the initial stack. So if you run that, that should be equal. So that means this mark and this mark should produce the same thing. So these are the equivalences we are proving. So it's like in a nutshell, it will be like this. So in every layer, these are the theorems. Theorems of interest we are proving. So there are many sublemmas are there, but these are the most important theorems which we are proving. So here we are using an SMT solver based tool, right? So graph reachability is a recursive transitive closure. So proof requires extra lemmas on an SMT solver to prove it automatically. So we have to come up with suitable precondition, invariance, and postcondition. And another challenge is that like DFS is running on a graph data structure and heap is on a linear data, mark is running on a linear data structure. We need to prove the program equivalence between the second proof. That program equivalence we need to prove. And the third thing is that concrete memory properties like no marks, because fixed length buffers are used in the concrete layer. So while doing the marking process, the stack can overflow. So we need to prove, we need to make the solver convinced that mark stack overflow will never happen if we set the properties suitably. So that proof also we have done. Otherwise, we won't be able to carry out the verification. And like in order to prove the functional equivalence, yes, yeah, okay. Yeah, that's it, sir. Okay, so it's that's it, and we have done several variants of our GC. I think that's it. It's already done. So this is our like benchmarking result, which shows that we are not inquiring. Yeah, fine, done, sir. That's it.
What was low star? I just missed.
Low star.
Low star.
Okay, so low star is like a subset of F star tool, which gives a C memory model kind of facility to write code. So it is like we can write similar like C code, like using loops, for loop, while loop, and all, with like fixed length buffers and all, like buffers in the sense that arrays, fixed length arrays. And what we can do additionally verification on top of that. Like there is no buffer overflow is happening. There is no like the low star code ensures that whichever buffer we are using, it is allocated buffer only. It's not a free buffer. Like we should not use any free block kind of thing. So those, it's like C plus verification. That is the low star tool does. It's a subset of F star. Yeah, it's a tool.
Yeah, I think this is very, hello. Yeah, I think
Yes.
it's very interesting work. I was initially wondering whether you were taking an existing OCaml
Oh, yes, sir.
implementation or
Yes.
whether you the implementation of the garbage collection in the standard OCaml library, or
Yes.
whether
Yes.
standard implementation, or whether you were going to define your own thing. I think your talk made that clear.
Yeah.
And I was also curious about what you were doing the verification in, and you made that clear that it's in F star, low star, and
Yes.
so on.
Yes.
I like the fact that you're actually not verifying OCaml, but you're verifying OCaml's memory footprint of any OCaml program during its runtime.
Yes.
So you've got that level of separation. So
yes.
of course, to verify OCaml's, you'll have to make sure that an OCaml program always maintains those invariants.
Yes. Yes.
Right?
Yes.
I wouldn't use the terminology. No. She's actually creating a verified GC.
Yeah. Proof by
As
convention.
opposed to verifying an existing GC. And you don't have to worry about model the OCaml program's execution at all. You just have to just say that, look, if the OCaml programs at any runtime snapshot, if it maintains those invariants and that memory model, then then the GC is going to. I was also curious if whether your GC can run in concurrently with the OCaml execution.
That is incremental GC, right? Incremental. That's our future work. Sir. It's like a stop the well GC initially.
Okay.
Yeah.
All right.
Sanjeev, maybe get back to you after this.
Yeah, I just wanted to. Yes.
We'll get back.
No, so I had just one question, which is that you are using F star and low star. All of these
Yes.
equivalence proofs are also done in F star, right?
Yes.
So one of the things is, what was your experience regarding the error reporting that you were getting from F star when suppose the proof is not going through, like some lemma is not strong enough or whatever?
Yes.
So was there at all an issue during the development process of this?
Yes. It's like develop. You mean to say if missing lemmas are happening, kind of thing, like
Yeah. While you're making this, the errors coming out of F star saying that okay, this proof doesn't work because, and then interpreting whatever that is.
Yeah, like when such situation arises, we need to find out what is the missing lemmas happening, like because we need to aid the solver with whatever missing conditions, right? So we need to intuitively find out what is happening, like what is missing, and we need to provide that actually. So like it's like a first work in graph based verification in F star. So naturally we will be having challenges because we don't have nothing to refer. So we like with the trial and error, with experimentation, we came up with all these things.
So I apologize for the overload of the session. So I think we can continue offline. Yeah.
Yes,
I
sir.
think we can leave for lunch.
Safety and liveness, you should use soundness and completeness.
Oh, okay, sir. Yes.
That's a more accurate term.
Yes, true. Yes.
Just to give you some historical thing in your slide 5. In 2000, with Shahgopal Narek and Kumar Neeraj Verma and we did a verified in-mock, verified garbage collector for the ordered OBDD packet that was going into itself.
Okay.
So, that kind maybe that's going to point out how.
Okay, yeah.
Garbage collection.
Yes, 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 sir. So it's like a correct by
Close the
construction.
session and we can
Yeah.
take the.
Yeah.
Okay, hello, welcome back to the third session of RSPL. So in this session, we will be having 3 talks, and we'll begin with the talk by Hari Govind from University of Waterloo. So yeah, without further delay, let's begin. So, Hari Govind.
Check. Is this good enough?
Oh, yes, can you comment?
Yeah. Shall I just start? Yeah. Hello, everyone. Welcome to my talk. I'm Hari Govind. I am a final year PhD student at the University of Waterloo. And my research is on fully automatic program verification. Yeah. So, okay. Yeah, so I don't have to motivate program verification to this crowd. I believe we have several talks on formal verification. I'm just going to introduce a kind of verification that I'm working on. It's SMT-based symbolic program verification. So in this setting, we have a program and a specification for the program written as, let's say, assertions in your program. And what we want to do is we want to mathematically prove that for all program behaviors, that is for all possible executions of this while loop and for all possible values of your input, the assertion is never violated. Okay. Okay, sorry, the mouse is just annoying. Okay, so the specification, we add the specifications as assertions in our program. And we can have things like, our program does not have any null pointer dereference. By just asserting that whenever you dereference a pointer, you assert that it's not null. Doesn't have division by 0. You just assert that whenever you divide, the denominator is not 0. And we expect the program verification tool to come up with a mathematical proof. And by mathematical proof, what I mean is that it will compute a formula that represents the set of all reachable states of your program, compute a formula that represents the set of all bad states, and it will prove that these two formulas are unsatisfiable. That is, these two sets, they don't intersect. And of course, you don't have to compute exactly the set of all reachable states. Any over approximation will do. But how do you compute this reachable states? Well, for straight line pieces of code, it's quite easy. So in the first 2 lines, it's just A0, B0. But the tricky case is when you have while loops, especially if it's unbounded. There, if you want to represent the set of all reachable states, because you don't know how many times the while loop executes, you have to summarize it using loop invariants. So loop invariants are predicates over state variables, and they are typically one-inductive. That is, they are true at the start of the first execution of the while loop. And if you assume that they are true at the start of an arbitrary execution, you can prove that they are true at the end of that execution as well. So they are closed under an iteration of the while loop. So typically, program verification tools are deductive. That is, they expect the programmers to come up with these loop invariants. But my research is on automatic verification tools. So these tools, they just take as input your program as well as your assertions. And they will come back and either tell you that the property holds, in which case it will automatically generate all the loop invariants that are necessary to prove your program safe. It might come back and tell you that the property does not hold, in which case it's going to give you a concrete execution trace that starts from the initial state and violates the assertion. Of course, this problem of reducing loop invariance is undecidable, so it might run forever or return unknown. I work, oh, sorry, I can do this, right? I work on the sort of back-end engines for automatic verification. Specifically, I work on a technology called CHC solving. Yeah, it's going to come up next start once this works. Okay, CHCs are constraint horn clauses. They are a fragment of first order logic. So it's a formula written in first order logic. And it's a really nice fragment in the sense that it doesn't have any quantifier alternation. And it is expressible enough to express all safety verification of programs. So the encoding itself is not that important for this talk. In fact, for the whole talk, I'm going to stick at a high level and explain all my ideas at the program level. So you can imagine that there is some straightforward translation from your program written in your language to this logical representation of your program.
Quantifier, a universal quantifier block, P1 and P2 conjunction implies
Yeah.
single.
Yeah. So this is a horn clause, so only one positive literal, and there is one predicate that is unknown that we are solving for. Okay, and CHCs are gaining popularity as a suitable intermediate representation for automatic program verification. There are several tools in this domain. In particular, I want to point out there's a tool by my supervisor, Ari Gurfinkel, called CHON. It translates C programs from LLVMIR into CHCs and uses a backend engine to solve it. And then there is this other recent work on Solidity, where they have a Solidity model checker that translates Solidity programs into CHCs. I've been interning at MathWorks, where I translated Simulink models from MATLAB into CHCs. But my research is on the backend engine. That is, how do you scale CHC solving? By scaling, what I mean is that I want the solver to converge more often. That is, I wanted to find loop invariants more often. I want them to be extendable to different domains. Like if I want to express things like algebraic data types, like lists or trees, or recursive functions, I want the solver to be able to handle those things. So in first logic, the theory is algebraic data types, and abstract data types is the, I guess, the programmer name. Okay, I mean algebraic data types. So, okay, thanks. And finally, most recently, I've been working on how do we get around analyzing complicated functions. We'll get to that at the end of the talk. Okay, so I have certain publications in along these three aspects. And in this talk, I'm going to talk about one of my early works on providing global guidance for the CHC solver. Okay, so a little bit of background. I'm working on top of a CHC solver called Spacer. It is based on the popular IC3 PDR model checking algorithm. Spacer is integrated into the Z3 SMT solver. So if you run Z3, you can run Spacer. And it's pretty much state of the art. It's been winning some of these competitions. And I'm not going to explain the whole Spacer algorithm. I'm just going to explain two fundamental steps in Spacer. And I'm going to explain them by just running Spacer on our XML program that we saw earlier. Okay? So Spacer fundamentally has just one main data structure. It's called frames. It's just a list of formulas. Okay? And it maintains the invariant that frame I over approximate set of states reachable in I iterations of your while loop. For example, frame 0 over approximate steps reachable without executing the while loop at all. And then here, frame 1, which is assigned true, that means that we assume conservatively that if you execute the while loop once, all states are reachable. And the way Spacer works is, as it makes progress, it kind of refines all these frames until it finds an inductive invariant. Okay, so how does it make progress? Well, the first step in Spacer is to check if init intersects bad. That is, do you reach the assertion violation without executing the while loop at all? So this is just a straightforward encoding of your int conditions as SMT formula, bad conditions as SMT formula. You're in some quantifier free fragment of some theory. You give it to the SMT solver. The SMT solver comes back and tells you that it's satisfiable. You have a 0-step counterexample. If not, you have you know that it's unreachable in 0 steps. So we check if the assertion is violated after one iteration of your while loop. This is again another query, a slightly more complicated query to the SMT solver. But if it tells you that it is satisfiable, again, you're done. You have a 1-step counterexample to your program. But if it's unsatisfiable, something interesting happens. You have a 1-step counterexample. We haven't used that at all. So right now, the only check we are doing is if you have init, you have an encoding of the body of the while loop. It's a concrete check. Yeah. And we are going to use this concrete check to refine our over approximation. So this is how you construct the proof. Okay. So if it's unsatisfiable, earlier we know something about the reachable states after 1 step. Right? So earlier I said conservatively that all possible states of your program are reachable. But now we know that bad is not reachable. So you can refine your first frame by saying that only states that satisfy not bad are reachable. So this is called a lemma, and we use lemmas to refine the over approximation. But yeah, so I'm just still in the phase of the algorithm. So this is one step of the algorithm. So, but when you learn a lemma, can you learn a better lemma? Sorry. So in order to learn a better lemma, Spacer uses this concept called interpolation. It's a well-studied concept in first order logic, in logic in general. Basically, an interpolant, if you have two formulas that are unsatisfiable together, an interpolant is basically a formula that separates these two. And in our context, in the domain of linear integer arithmetic, if you have two conjunction of literals, then you have two convex sets, and an interpolant is basically a separating hyperplane. Okay, so here with the blue arrow, I have denoted the set of states satisfying this blue part of the formula. The orange region is a set of states satisfying the bad states, the orange part of the formula, and these two are unsatisfiable together. That is, they don't intersect. And an interpolant is any hyperplane that separates these two sets of formulas. Okay, and the interpolant actually generalizes bad. So earlier we said bad is unreachable. Now the interpolant says that not only is the small triangle region unreachable, this whole big rectangle region is unreachable. So the interpolant allows you to generalize things that are unreachable in one iteration of a loop. So you learn the lemma, and with the lemma you can refine your first frame further. So okay, so you're done with one iteration. So you prove that bad is. Yeah.
Just take the complement of what you could reach in one step.
Oh, so that involves quantifier elimination. So if you want to compute exactly the set of states reachable in one step, here it might be easy, but in general that's how. So this is just a satisfiability check and an interpolant based on the proof of that step. So this is easier. Yeah, that we'll get to. Okay, that's a brilliant question, and that's one of the answers that we will answer later in the talk. Okay, so Spacer proved that there is no counterexample in one step of your while loop. How do you prove? Now, the next step is to prove that is bad reachable in two iterations, and this is where things get really interesting. So Spacer does this incrementally instead of just having a single query. It does this using multiple queries. It computes what are known as predecessors to bad. Predecessors are basically any states that reach bad in one iteration of your while loop. Okay, so an example would be a equal to 3, b equal to 4. So if you assume that a is 3 and b is 4 at the start of the while loop, you can imagine a value for k, example 1, that reaches a bad state. Okay, so any such state is a predecessor. How do you get predecessors? Again, you just ask an SMT solver what is the satisfying assignment to our while loop. So Spacer doesn't exactly compute predecessors. It computes a generalization called a proof obligation. And there is a really nice algorithm called model-based projection to do this. I'm not going to go into the details of this, but we can discuss this if you're interested later. Okay, so let's say we computed some predecessors. Now what do you do? So we already saw how to block bad in one iteration of your loop. Now we can do the same thing, but for the predecessor proof obligation. Okay. So you recurse, you do the same thing, you call an SMT solver, you interpolate, and you learn different lemmas to block different proof obligations. So once you have exhausted all the set of predecessors for bad states, then you can actually prove that bad is unreachable in 2 steps. And with that information, you can refine the second step. You can refine the second frame. And this is how Spacer makes progress. It continuously refines these frames until you find an inductive invariant. Okay, so the key takeaways from Spacer is that it has 2 main steps. One is learning lemmas using interpolation, and the other is computing predecessors, and that involves getting a model from the SMT solver. Okay, so this takes me to my first contribution, which is providing global guidance for the interpolation algorithm. Earlier I mentioned interpolation. Interpolation is fantastic. So there are a lot of SMT-based model checking algorithms that use interpolation. And one of the reasons why it's so good is that it can come up with these magic terms like a equal to b, even though you have never seen a equal to b in the transition system or initial state or bad states. Interpolants can come up with these magic terms. So interpolation is quite good, but there are too many interpolants. So interpolant is just any separating hyperplane. So you can have multiple set of interpolants, but sometimes you can have infinitely many choices, but we don't know how to choose a good interpolant. Okay. So how does it affect spacer? Well, if you have some slightly tricky example that I've seen here, I'm not going to explain this example. I'm just going to explain what happens when spacer runs on this example. So if you look at the log of spacer, you see some patterns. You see that spacer learns a bunch of lemmas that are very similar to each other. For example, here it says that there is some term that is less than 0 implies some term less than 0. Then same term less than 1 implies same term less than 1. Then same thing with -1. You let it run longer, you can see that the kind of lemmas it learns, there is a pattern to it, but it just keeps on learning the similar lemmas over and over again. So what is happening here? Each of these lemmas are returned by the interpolation algorithm, and the interpolation algorithm thinks that these are good lemmas to learn because it only sees one of these proof obligations. So it's just one, it's local in the sense it only sees one proof obligation. But from a spacer perspective, we are trying to construct an inductive invariant. So we know that if we learn more lemmas, we are going to diverge. Okay, so this is the problem with interpolation. The problem is that it's not aware of the inductive proof that spacer is constructing. In our paper, we described 3 different algorithms for 3 different problems with interpolation. Sometimes it generalizes too much, sometimes it generalizes too little, sometimes it generalizes in the wrong way. I won't explain these examples. Instead, I'm just going to focus on our solution. So our solution is to provide global guidance to spacer. That is, whenever you learn a lemma, use the context of spacer, use the state of spacer, the set of lemmas that spacer learns, the set of proof obligations that it has seen, in order to generalize the lemma. So what it looks like in this example is that if you look at the set of lemmas here, you can see that there is a pattern. And how do you summarize this infinite set of lemmas? Well, you can summarize it using something called the convex hull. You just compute the convex hull, and then you learn one lemma that summarizes all these lemmas. So this is one rule for global guidance. We call it subsume. We have 2 other rules, conjecture and concretize. These are explained in the paper. Okay, so this is slightly complicated. So these are not convex sets. So if you take the negation, you can see that this is a conjunction of literals. And then, so this would be these regions here. So these are the convex regions, so the white part here. And then you compute the convex closure, which is the negation of this purple part here. So the convex hull of the lemmas that you learned so far. Yeah, so as spacer makes progress, once it learns 10 lemmas, we just try to compute the convex closure. So there is some heuristic on deciding when to compute the convex closure. Okay, so we implemented this on spacer. First we supported linear integer arithmetic, and we ran it on a bunch of benchmarks, and we got some good results. More importantly, this was integrated into Z3. So if you run Z3 from the master branch, you can run global guidance. And then we try to scale it to different theories. So kind of similar techniques will work for linear real arithmetic. Then we did it for bit vectors in a different paper. We also support arrays, global guidance for arrays. But then when we start handling more complicated theories like algebraic data types or nonlinear integer arithmetic, we struggle. And the reason we struggle is something that is fundamental to spacer. So let's take an example. So here I have the same program from before, but now I have introduced some more complicated things, some nonlinear arithmetic here. And the reason spacer struggles is in this getting predecessors for a proof obligation step, right? So there was 2 steps. One was to generate a model and compute a predecessor from it. In that step, you have a query in an undecidable fragment of logic. And therefore, we may not get a model for this formula, and therefore spacer can't make progress. So let alone forget learning lemmas and diverging because you learned the bad lemmas. It can't even learn lemmas. Okay, so how do we overcome these complicated functions? Well, typically what you do is you try to abstract them away using more general functions. So here I introduce uninterpreted functions as an abstraction for the complicated nonlinear arithmetic. And with this abstraction, we get back decidability. But then we lose something called quantified elimination, which means that we cannot make progress. Okay. I'm not going to explain this further. We are almost out of time. So I'm just going to explain some of the ongoing work. So the ongoing work is that we are trying to handle this abstraction inside spacer. So as spacer solves more problems, we want to see if we can do this abstraction in a nice way so that we get both decidability as well as the same guarantees that spacer used to get. Okay? And we show in a Popel paper how to do this for this domain, the domain of algebraic data type and recursive functions. And then we sort of, this is our most recent CAP paper. We describe how to start reasoning about uninterpreted functions from inside space. I want to emphasize that this is still ongoing work. We don't support nonlinear integer arithmetic. We are actively trying to do this. So to summarize, I work on automatic program verification using constraint Horn clauses, and it's getting popularity. I work on the backend engine. I want to make it more scalable, that is, converge more often, extend to different domains, and analyze complicated functions. And I presented sort of my first contribution, the global guidance to improve this lemma generalization. Finally, I just want to acknowledge all my collaborators. They do wonderful work. That's it. Thank you.
So we have time for one quick question.
Yeah.
So the lemma that has been learned by a convex hull, it is just from some of these sort of examples you've seen. So do you have to check that it's correct at any point, or is it guaranteed somehow?
We only so you can apply convex hull for any convex shapes, but then that would be expensive. So we only we apply it in a restricted sense. So we know the kind if the lemmas belong to some kind of syntactic patterns, we apply the convex closure. We know that computing the convex closure is easy then. But then we also have this notion of syntactic convex closure, which uses this notion of quantified elimination to do more complicated convex closure. But we try not to do it because it's expensive.
Okay, so let's thank Hari again for the nice talk.
Do you know how to? I have this open. Should I just drag it? But I can't see it there. Should I just drag it here? Do you know how to show? No, but that was a PowerPoint. So when I just clicked present, it just worked.
Do you have to go presentation mode or something? No, like
Yeah, yeah, it is a PDF. Yeah, just.
We can.
Okay, so our next talk of the session is by Abhishek De from University of Birmingham.
Yeah.
So, yeah, Abhishek.
Thanks, Abhishek, for introducing Abhishek. This is right. I'll hold it here. So this is a joint work with Luc Pellissier and Alexis Sona. I have been exploring this in my PhD, and this work has kind of stagnated of late. So it's secretly a talk in logic, but I would try to keep the logic as secret as possible. Yeah, okay. So semantically, the point is, let's say we have a monotone operator, and the principle of induction says that if something is post-fixed point, then the least fixed point is below that. And the principle of co-induction says, kind of dual of it, is that if it is a prefixed point, then it is below the greatest fixed point. And this sort of mathematical intuition allows you to define co-inductive data types, such as like streams, non-well-founded trees, and so on. So usually we define recursive functions using inductive data types, whereas we would like to define co-recursive functions over co-inductive data types. So this talk will be based on COC, in the sense that I will be using toy examples from Coq. I don't know how well that generalizes to other proof assistants. So the point is that proof assistants and some functional programs in general give you a sort of guarantee. It takes away the freedom from the programmer and instead gives you a guarantee that if you are able to compile the program, you will get good guarantees like termination for recursive programs. And it is done by some sort of static methods. So a guard condition usually, which ensures termination for recursion, and it's basically like a static call graph analysis. So let's look at this function, which is now in the realm of co-induction. So you take a natural number and you produce this infinite stream of natural numbers from n, right? And I give you two ways of implementing this function. So first, you do a cons of n, and by co-induction, you have f of n plus 1, and you just cons these two, right? Another one is saying that, well, we do kind of the same thing, but somehow by co-induction, we get the head of g of n plus 1, which is n plus 1. So basically, we get the n by subtracting 1 from it. And then, oh, sorry, there's a typo. That will be g of n plus 1. And so here, it will be g. So these are like two different definitions. Nothing mutual is going on here. So the question is, should we accept both of these functions, one of these functions, none of these? Can they prove the RQ one? Yeah. And this is the notion of productivity, which is the dual of termination in co-recursion. So productivity says that although your output is infinite, you are producing finite segments of that output in finite time. And so in this case, since at least in the first one, you have n, and you're consing it, at least you have n. So if you want to produce some part of your result, you can do it. But for G, it's doing nothing basically, because when you are looking at the head of Gn plus 1, and you have to fire Gn plus 1, you again have to fire the head of Gn plus 2, and it just keeps going deeper and deeper forever without really producing anything. And so ideally, we would like a functional program to say that I accept F and I reject G. Coq does that. So this is, there are some artifacts of Coq here, but basically you can see that these look quite similar to the mathematical definition I gave in the previous slide. So you're consing n with f of n plus 1. And in this case, you are matching, you're pattern matching Gn plus 1 as cons of some head and some tail. And you are saying that what you produce is cons of head minus 1 and G of n plus 1. And as you would expect, Coq accepts the first one and rejects the second one. It won't compile. Because it would fail the sort of guard condition. So it does this sort of static analysis. Right. So what about the
basically say I can't calculate it. I don't know. The Coq front end itself.
Yes, so, but that's the interesting thing, right? It is saying I cannot compute this without actually computing it. So that's the beauty of, let's say, typed functional programming in a way. So if there's one thing you want to take away from that. So what about this next one? It does some jugglery with lets and matches and everything, but it basically just does the same thing as F, but instead of simply consing with f of n plus 1 like a sane person, it says that, well, f of n plus 1 looks like cons of h and t. Because you match, oh, I can use the pointer. So you can match f of n plus 1 as something like cons of h and t. But then you are producing cons in h of t, so that's fine. And we, as programmers, would expect that Coq should accept this, but Coq says that there is a possibility that this pattern match goes into an infinite loop. It keeps on pattern matching and never really produces anything. And so Coq rejects this. So our program started out as a way of making Coq smarter and trying to accept these sort of things. And this is where the secret logic comes in. So I want to see this through the Curry-Howard isomorphism, where formulas are types, proofs are programs, and cut elimination is computation. And so I would transfer this into a question of proof theory and ask, can proof theory give me some answers about this? And we will talk about a logic of mu-mal, where you can encode these co-recursive and co-inductive and inductive data types as formulas using fixed points. In this situation, if you were in Anupam's talk in the morning, we saw cyclic proofs, and we will see these co-recursive programs as cyclic proofs. And there's a notion of progress in cyclic proofs, which I would like to see as guard conditions. So I will accelerate at this point because I have 5 minutes left. So I was supposed to give a crash course on mu-mal, but I wouldn't do that. It's just that you have least and greatest fixed points, generalized fixed points on linear logic, and proof trees are infinite now. And proof trees is a proof tree is progressing if every infinite branch there's a thread satisfying the parity condition, and checking if this proof is finitely representable, then checking progress is p-space complete and most importantly decidable. I would skip mal, and you can see this program as a proof like this, and it is progressing because it has a sort of progressing thread which satisfies the parity condition. And we would like to say that, yes, Coq should accept this program. Whereas the other one, it does not have a progressing thread, and Coq rejects it. So it goes as we expect. But the question is, can we do the other one, which was the problematic one? And here, even in the logical side, it is not progressing. So we didn't achieve anything. But now, a new paper, which is not by me, it's by David Bald, Alexis Chona, and Amina Dumin. They propose this sort of bouncing thread validity, which says that, well, actually, I do validate something just by going through some finite detours in the proof. But this somehow is too strong. It's not the answer because, first of all, it's not stable under permutations. So if you just do some basic permutations in the proof, it somehow becomes not progressing, and checking progress becomes undecidable. So this is where we come up with another logical solution. We say that since this business of permutations come into the picture, it's very natural to consider a formalism of writing proofs where proofs are no longer trees, but they are graphs like this. And so you get rid of all this business of permutation, and we introduce a notion of non-well-founded proof nets, and we do cut elimination in that. So this is a series of work divided in 2 papers. So finally, what we would ideally like to do is define cyclic proof nets, define this notion of bouncing threads, and take it from the level of proofs to the level of proof nets, hopefully recover decidability, and then profit. Thanks.
Thanks. So we have time for a couple of questions.
For the two references are DS.
D is me. Sorry. Sorry. Oh, yeah. Oh. Yeah, so this is me, Alexis Sona, and
Where does it appear?
this is Tableau, and this is PPDP.
Yeah, any more questions? If not, let's thank Abhishek again.
Cheers.
This is just you all get together and do something.
Yeah.
Storm the world, not shake the world.
So the next talk by Abhishek Shankaran from TCS Research, talking about program verification using small models. So yeah, Abhishek, please.
Yeah, this is the click. Okay, great. Laser pointers. There's no laser. Oh, yeah, laser. Oh, great. Excellent. Okay, great. Thanks, Abhishek, for the introduction, for the kind introduction. Thanks, Abhishek, for the very nice talk. Hi, this is Abhishek. We rigged this. Okay, so yeah, good afternoon, everyone, and thanks for coming for the talk. What I shall be going to give you, speak to you about is program verification using small models, which is an approach which we're just exploring at TCS Research in trying to use methods from mathematical logic model theory in the verification of programs. Okay, so very quickly, well, most of these is just known, but just to formally state this. So the program verification problem is given a program P and an assertion A. Is it the case that for every input I, the assertion A holds at the end of the execution of the program on I? If the program does not terminate on I, fantastic, because the assertion holds vacuously. So the assertion, the problem is really non-trivial only for those inputs for which the program does terminate, at the, in which case we would like to check whether the assertion is true. Now this problem is of course undecidable. This is shown by Turing, but that has not stopped the world from attacking exactly this problem, and even industrial labs from attacking exactly undecidable problems. So there are plenty of tools, immense number of tools developed for this. Variabs is one of them. We are just exploring the use of methods from a branch of mathematical logic and model theory in investigating this problem, just an exploration. Okay, so translation into logic, how what's the overall approach? Well, given the program P and assertion A, we will encode these respectively as sentences phi P and phi A of first order logic over a suitable vocabulary. Okay, now what is the property of these particular sentences? In what way would they correspond to the program or the assertion? Or so the sentences would be such that over the class, whatever mod phi x is, the class of all finite models of a small set of axioms, small set of first order axioms. So I will just call this. So it's like saying all the statements to follow are going to be relativized to this universe. This universe is the class of all models of this particular sentence, or this set of axioms phi x. So the short term for that will be modulo phi x. Okay, modulo means remove everything from the universe. Only the models of phi-x are the ones that stay, and all the statements are over the class of models. Okay, so modulo phi-x, the following statements, the following things hold. The models of phi p capture precisely suitably abstract representations of the execution of the program P for arbitrary inputs, which means if you were to run the program P on an input, it would correspond to a particular model of phi p, which is inside this particular class of models of phi-x. Okay, so every execution, concrete execution of the program translates to a model of phi p, and conversely, every model of phi p that is inside the class of models of phi-x corresponds to an actual execution of the program on the input. Okay, on some input. So this is like a one-to-one correspondence between the executions of the program on inputs and the models of phi p. Okay. Likewise, that's for the program. Now for the assertion, the models of phi a and phi p precisely capture the set executions of p that satisfy a. Okay. So if we take a model of phi p, which is a model of phi a, then that corresponds to an execution of the program that satisfies the assertion, and vice versa. Okay. So this way, this is the correspondence between the program assertion and the logical side. Okay, so how does the verification question translate? Verifying whether the program P satisfies A then translates to checking modulo phi-x. It's always the universe. Okay, the validity of the first order sentence phi P implies phi. That means every execution of the program must satisfy the assertion. Equivalently, this verification translates to checking modulo phi-x, the satisfiability of the negation of the sentence. Okay, so now entirely the program has been translated to first order logic satisfiability. However, unfortunately, first order satisfiability is undecidable. Okay, and this is known first order satisfiability in the finite, because we are interested in finite executions. This problem is of course undecidable. It's RE, and this is shown by tracking brought in the 50s already. Yes, Suresh. Yeah, so it turns out that phi-x is just a very simple set of axioms that encode linear orders and talks about successors and talks about the fact that the predicates that we use to model the variables of the programs are just functions. Okay, so they are just a small constant, sized set of axioms, very small set of axioms. They're a function of the vocabulary that we use, which is just proportional to the number of variables in the program, and that's about some constant times that. Yes. But you see, finite set of axioms. Yeah, well, we will of course restrict to very simple class of things. But I presume, but I'm pretty sure, because the encoding that is there is very much like the encoding that is used in the proof of tracking Rod's theorem or in the proof of Fagin's theorem, which starts off with an arbitrary Turing machine. So I would presume that this would still work. But of course, how large, that will depend upon the kinds of features that are there in the program. Okay. Okay, so that's the thing. So this is an undecidable problem, but we explore the use of a particular model theoretic condition known to give decidability results in the logic called the small model property. Okay, what is the small model property is something that you know, but let me formalize. We say that a class of sentences of the form phi a and negation phi p and negation phi has a small model property if what you intuitively expect is actually true. Namely that if there's a nice function f on the natural such that modulo phi-x, the following implication holds. If there is a model for beta, that particular sentence, if there is a model, then there is also a small model, where a small model means a model of size less than equal to this function applied to the length of beta. Okay, which basically means therefore that if you read this, either you start off with a model, if you're looking at a particular model of beta, either it is already small, or it is the case that if it is large, then there is something else that is there which is small and which satisfies beta. In summary, this implication is saying that either modulo phi-x, there are small models for beta, or there are no models for beta. Okay, either there are no models or there are small models, which is good. Okay, this whole thing in the context of the program, what does it mean? From the perspective of P and A, this translates to asserting the existence of a small execution of P violating the assertion on some input, and hence on a small input, because after all, in a small execution, it's only a small part of the input that can be accessed, and so you can remove the rest of the input, and that's the small input that you get. So there is a small execution of P violating the assertion on a small input, if at all there is some finite length execution of P on that violates A. Okay, that is what this whole implication seen from the program point of view reads as. All right. This implication gives a complete decision procedure to check if beta is satisfiable or not. You just enumerate all small structures and check. If you get something, great. If you don't get something, you know that there is nothing, there's no model at all. So this is where, this ties to Raghavan's talk yesterday, the part where, we can put a number and try and check for all models within that bound. But if we can get a guarantee that the number that we give is like complete, then that will be great. Of course, significantly, this would be a harder problem as well. So it would even restrict the class of things that we can do the analysis for. But nevertheless, if we can do it, then it becomes a complete decision procedure. Okay. And of course, in theory, nice means computable, but for all practical purposes, we want real small bounds like less than 10, okay, which would make things work. Okay. 5? Yeah, I think that's exactly right. So what we'll do in the remaining time, in the remaining 5 minutes, is just take a particular example of this min program, which we did in like 5th standard or something. Okay, and so we want to show that this particular program, which computes the minimum of an array by computing the minimum of the initial segments of the array in an incremental way, is actually correct. Okay. So the sentences for the program and the assertion which says that the value computed by the program is actually the minimum, that can be constructed. These are all sentences over a these are all multi-sorted first order logic sentences over a suitably chosen vocabulary. Multi-sorted means multiple domains. Okay, it's just syntactic sugar. I mean, essentially this is just first order logic. Okay, so the main results are, let P be the min program and A be the min assertion. The theorem basically says that if there is a finite model for phi x and phi p and negation phi, then there's also such a model in which the sizes of all the domains interpreting all the sorts is bounded by 7. Okay. Equivalently, if for some input from the program point of view, if for some input array the execution of the min program violates the min assertion, then there is also such an input array of size at most 7. Okay. We can make this better. We can make this at most 3. We can make this secretly even better. We can make it to 2, but I will not. But that is just to keep it to yourself. Okay, so that's the main results for the min program, and here is how the intuitive idea. The intuitive idea is just this: you consider an array with just 3 elements, so 7, 3, 5. The m uninitialized min program, okay, which is the one where you don't say m equal to a0 at the beginning. Okay, it's some arbitrary value of m to begin with. This m uninitialized min program can be seen to be defining a function f from the input values of m to the output values of m. Yeah, there is some value of min with which you come into this particular program which operates on this array. Then there's some array computation, something happens, and then there's a final value of min. So this function min program can be seen to compute a function from input min to output min, given this particular array. Can we construct another array B of size less than that of A, such that the min program, when it runs on this particular array, computes the same function from input m to output m? Do you have any quick guess? Can you do this particular thing? Can you construct a smaller array, strictly smaller array, which also computes the same function as the min program does on this array? Array with just the min element. Okay, great. Okay, you've gone one step further. Great. But there's a line missing. But one quick first approximation is you just take the minimum of 7 and 3. Okay, you reduce the and then you put that as the first element of the array, and then 5. Okay, and as you got it right. Exactly. So you can just take the minimum of all of them, and that's your array, single element array. Okay. So this is true. So with this one single element array, you'll compute exactly the same function. So now, if there was a large array A on which the min program execution does violate the min assertion, suppose this was the case. We don't know how large. It's some large. Okay. So this is something of this form. I don't know why those last end markers. Oh, they are there. Okay. So this is some big array. Okay, but this is violating the assertion, which means, so this is the array, this is the sequence of min values computed. Okay, last min value is mn, but this is violating the min assertion, which means there is something in the array at some position which is actually less than this value. Call that as vk. Okay, so vk is of this particular form. Now, because it's a very large array, but vk is just 1, by pigeonhole, you know that one of the 2 segments, it partitions the array into 2 parts, one of which is certainly large. Okay, so let's say the right hand side is large. Let us look at just the segment of size 3. This segment of size 3 is much like the array A that we were looking at in the previous slide. Okay. Now, what we will do is we will take the minimum, as you just said, we will take the minimum of that particular 3-segment array. And you now observe that if I were to replace those 3 elements with this one single element, and if I were to just look at the sequence of min values that was there, removing the corresponding min values that were computed, then this is actually an execution of the program on this array. Because this is an arbitrary MK value, and it operated on this 3-element array, and it computed an output value which is MK plus 3. But this reduction that we did was an IO preserving reduction. It was an input-output preserving reduction where we removed this entire element segment of the array of length 3 and replaced it with a segment of array of length 1, and we would get MK and MK plus 3 exactly. With the result, when the min program continues, it will continue as if it continued just before. Yeah, it does not know that the change was made. Okay, but it will still continue to produce the same min value as Mn, and the relationship of Mn with Vk will still continue to hold, namely that it is greater than Vk, and therefore this shows that this is another input on which the program is, yes, it's a bug. Oh, no, this is all the min values. This is the array. Okay, these are those partial min values. So therefore M minus 1 is A0, M0 is the minimum of B0. Say, exactly, it is the same K, yeah, it is the same MK. It would have been the same even without the transform. Yeah, exactly. Exactly. So this was the original thing, that was MK. After the transformation, it was still MK. I'm sorry, it was still MK. Sorry. Yeah, after the transformation, it is still MK. Okay, and likewise, MK plus 3 is also the same. It was the output of the functioning of the min program on this 3-element array. And we have ensured that by this particular choice, we have ensured that if it was MK, then it is MK plus 3. Okay, so therefore the min program will continue exactly the same way and complete, and so therefore it will produce exactly the same Mn value. Therefore the relationship with Vk will be the same, and therefore this is another array on which this whole program, which witnesses the bug in the program. Okay, with this reduction, which is a strict reduction, we can recurse on this. Yeah, so this is true. We can recurse on this, doing this reduction on either side of Vk, on either side of Ak, and eventually we get this array below, which will be of the form which says Mn, the min value computed on this array will be still greater than Vk, but it is an array of size 3. Okay. In fact, yes, it's almost done. Okay, great. Yeah. So in fact, you can get it down to even 2. Maybe just subsume min with take the min of the first 2 elements, and then So this is great. So I'm done. This is great. So the min program and the assertion pair has a small array of size 3 witnessing the assertion violations, but we are still not quite done. We can't still enumerate all arrays of size 3 because we can't even enumerate all arrays of size 1. There are infinitely many of them. How do we check for all arrays of size 3 for assertion violations? And here is where we make some observations about the min program. The min program does only comparisons of values. Therefore, the number of order types of 3-element arrays is small. Okay, look at the number of linearly ordered elements which have 3 elements, which are labeled with natural numbers. What are the number of ordering relationships between them? There's only finitely many. I think you can verify that it is 7. Okay, or of the order of 7. Okay, so therefore, if that is the case, we can simulate all those comparisons only on arrays whose elements come from the set 0, 1, 2. All such comparisons that are there on arbitrary natural numbers can be simulated on just the same on this set, which is just 0, 1, 2. And that's a small set now. We can run Z3 on this, and we'll get our answer. Okay, so that's our proof. Okay, so I think I have, so that was the intuitive idea. I think this whole approach that is there is simply generalized to a larger setting where we have this full pipeline workflow. Okay, and we kind of do this reduction thing that I spoke. We knew what to do because it was a min program, but it's an arbitrary program. What do we know what to do? That's where we will use the SAT solver. We'll do all this combinatorial reasoning. We offload it to the SAT solver. Okay, this is step 2. This is the crucial part of this entire pipeline. Once we get this, once we get this K, then we will do some model theoretic analysis, and then we'll get a number Fk, which is the small model bound. Once we get Fk, we just check for satisfiability in all small models. Okay, so the parameters, yeah, okay. I think Abhishek is half a minute. Yeah, perfect. So parameters, yeah, parameters are fine. Just one quick thing. If we have gotten the small model bound, when we run Z3, suppose Z3 returns SAT, then we definitely have gotten a violating input. We have a bug. Yeah, we have a trace. But if Z3 returns unsat, so if Z3 returns SAT, I can convince the person who has given me the program, look, this is an input. You run the program yourself and see there's a bug. But if Z3 returns unsat, how do I convince the other person that, look, the program is actually correct? I have only checked for small inputs. How do I convince the other person that the program is actually correct? It is here that we will have to do something more. Namely, that we can pass the unsat core of this particular formula that we fed to SAT Z3, but we will also need to give that proof, the reduction theorem proof, that if there is a large model, then there is a strictly smaller model. So, which is also strictly small structure, which is also a model, so that you can recurse on this and get to a small model. That proof needs to be provided. Okay, which is what this particular statement says. An inductive proof over L greater than or equal to f of k of the statement of the counterpositive of this reduction theorem, that no model of size less than or equal to L implies no model of size less than or equal to L plus 1. And this is where, I was just discussing with Anupam, this whole thing can be formulated in, we would like to do it in Coq. Okay, and the important point is that all of this reduction is constructive. So that's a very good thing, because even the counterpositive is constructive, and then we can do some very nice discussions and ideas from Anupam on this. All right, so that is all. We did some experiments, and we have very initial stages of these experiments, but some encouraging results there. Okay, future work. We have a class of programs for which we believe this lives. We just need to write this down, and we have some extensions. The last of which is very exciting, which is graph algorithms. We have been thinking about this, and it'll be cool to make some progress on this front. Okay, so Dhanyawad.
Yeah, understood. So we are already out of time, but maybe we can ask one.
Yes.
One quick question. Okay, so thanks, Abhishek, again.
Thanks, Abhishek. Thank you.
And before we leave for the break, we will have some word from Deepak.
Yes. Deepak, before your word, one quick announcement can I make? Yeah, because you should have a final word. So the thing is, I think because of this, for RHPL, we are gathering together talks where there is a good bit of theory, and we are also developing tools. So many tools are being developed. So we felt that it would be a good idea to know what are the tools that we as a community are developing. So we have kind of put together one. You might have received a mail from Karthik about that. There's a Google form on which those who have their tools, or those which are still upcoming, which are not fully made but are still upcoming, or which are made, please fill in the details of the tool and all the details that have been asked for in the Google form. We will collect that and make them available on the website, so that if I'm working on a certain area, I want to have a tool, I can approach some friends of mine who are there, and we can work to make these tools happen here. So request that. Thanks.
Thanks, Abhishek. So just wanted to have a few points to discuss, and maybe also thank the organizers. Some of us may not be here after the lunch, after the tea break. Please do come back for the last session at 3:30. So yeah, so as you all know, this RHPL, we started it in 2020, and then they took a break during COVID. And the main idea was to kind of try to get back the programming languages and practical verification into FSTTCS, which is kind of dropped off over the years, even though it is very much part of even the title of the conference, software technology. And so that was the aim, and we thought we'll run this workshop for maybe 2-3 years, and then maybe try to have a separate track, provided the steering committee gets convinced and stuff. So a couple of things. One is we want to know, was this workshop useful for you guys, and what if not, then what can we change to have, let's say we have it next year, then. So any quick things that you all would like to, any suggestions? Or? Okay. The length of talks can be improved, or I guess we don't have much choice. So one thing was that we said we would shortlist some number of talks based on how mature the work is, where it's published and stuff. But this time we kind of try to accommodate all the talk proposals that we got. So we managed this time, but maybe next time we might have to actually do some shortlisting. Yeah, Abhishek. With good probability, it'll be up, and Abhishek was asking questions. High probability. Right. That is one issue. There's a bit of, there'll be some kind of clash of interesting topics. Yeah, but I guess any parallel kind of thing is bound to have that. But yeah, we could, we could try to group areas. Try to kind of synchronize the areas between the two tracks, which we didn't really do this time. There was not a lot of, yeah. Right. Yeah. Okay. Okay. Right. Maybe overlap in one day, and yeah, that's also. No, we'll still have 3 days, but I mean, Vaishnavi is suggesting that we have like 2 days before and then one day overlapping, or one day before and two. But yeah, there'll still be some overlap. Yeah, that's another issue. Yeah. Workshop. Yeah. But typically not, I mean. Hmm. Yeah.
Come back to the question of why programming languages and logic. Logic in the sense of proof theory and
Right. Solvers. Hmm.
sort of all in all from
Track B.
when in fact the first thing
Hmm.
I know old timers,
Right. Right. So the question is how, how do we fix that? Yeah.
of course, someone mentioned that you need more PC members who are in that, which used to be the case.
Yeah.
But then the number of not
Yeah.
I mean, it'd be 4 or 5 members.
Yeah.
But it will still be comparable, maybe few more others. Or actually more track B.
It used to be more track B, yeah. Now it's overwhelmingly more track A. Yeah. Hmm. Right. So yeah, I mean, this was. Hmm.
This sounds a valid purpose. Yeah, it sounds a very good purpose.
Okay.
No, this sounds a very good purpose of bringing to attention what which is already got accepted other functions. But to have still, to recover at least two sets of years where new work.
Yeah. Yeah.
And I would find this is taking place after the government.
Yeah.
So I would like that it would be challenging to get this kind of response next year. So 1 year collect up
Right.
work that happened that got published.
Yeah, but hopefully there'll be, I think we'll reach out to a larger, right, but the community in the country is also large. I mean, it's not just the people who, so. Yeah. Yeah, that we can do, yeah, some amount of synchronizing between the, reduce the clashes. Yeah. Yeah, the only thing is, yeah, I mean, we can do that in RHPL, but if it's a track, separate track in the conference, it'll have to be more. Yeah. Okay. Mm. 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 Yeah, yeah, that's another thing. We could. Mm-hmm. Right. Yeah, Abhishek. Oh, sorry. Anupa, Anupa.
But another thing is the depth of perception outside India. FSTTCS is not where I would set up PL.
Right.
So maybe in school papers that particularly well known papers in this area.
Right.
Couple submissions was the spiral right?
Right.
So
Right. Yeah, we did that in 2020, and maybe this year we didn't do it as much of publicity, but yeah, we could have like a special theme, like a focus theme for the conference. Yeah. Okay. Anything else? So yeah, so if there was a third track in FSTTCS, how many of you all would actually submit to a PL track in FSTTCS?
So it's actually a PL.
Yeah, yeah. Right. Right. Sorry, what is the question? Right. So, okay. So, I mean, I think one thing is that, I mean, for whatever reason, track B has got this, that it's a theory, track. And we've been trying to, including, PL PC members and having this focus theme and stuff for the last few years, but it's not really impacted. I mean, like this year, there were 0 papers. I mean, maybe there were 4 or 5 submissions in the area, but none were accepted. So I think having a third track will say that we are serious about having this, and it attracts more visibility. People see that there's a third track, and that there is.
There's also a danger of just having whereas together they might.
Yeah.
Just by putting the same situation back, you're not going to
Yeah. Hmm. Okay, so anyway, we'll have to see what can be done. Yeah. Hmm. Yeah, and I mean the other thing is that track B already has a lot of good submissions. I mean, I don't think they have any issues with. They may not have as many as track A, but the final filtered papers they have enough for one separate track. I don't think that is going to change. I mean, yeah, I mean, whether we want to merge it at all is a question. Yeah, just continue as 3 separate tracks. But yeah, I mean, I think that's something further down the line which we'll have to worry about. Okay, so also wanted to just thank the organizers. So the main organizers for RHPL this year were Karthik and Madhukar. So they've done an excellent job. Let's give them a hand. So there were also a few of us in the organizing committee, including Abhishek, then Uday Khetkar, and Avik Roy Chaudhary, and Uday and Ganesh and Ramalingam, and myself also. So I think also let's thank the organizers, the Triple IT guys here, especially. Let's give them a big hand. So they've done a great job with the logistics and also recording things on, streaming it on Zoom. Take care. Thanks to all of you. Please don't forget to come back at 3:30.
Hello. Okay. So I need to. You can. I think yeah. Good. So I'm not too worried.
So final session.
Hmm? I think I should. Think I should announce for the last session there is a perk. Those who have attended, I'll remember the faces. If any day you apply, I'll be the one helping you out. Let's wait for a couple of minutes. I think it's last session anyways. Unless you want to. Okay, okay. No hurry, no hurry.
Welcome to the last session of RHPL. The first speaker of the session is Devesh Unadkar
Sure.
from Synopsys. Over to you.
Thanks, Pritham, for the introduction. Hi, guys. I'm Divyesh, and today I'm going to talk about program correctness. This is the joint work with Professor Supratik and Professor Ashutosh from IIT Bombay. I did this work during my PhD, and then I was affiliated with TCS Research. Okay. So I think I don't need to motivate this crowd because we all know that verification is really important, be it aircrafts or Tesla cars. We really want to save these systems from messing up. And so that is where most of us are coming up with newer and newer techniques. An interesting thing about these systems is that they are inherently complex and they use software to control their operation, right? So an important thing that we noticed is that a lot of these programs, they use arrays to store the data that is coming from sensors or batteries and battery cells and so on. And that data is then processed to take several actions. Some of these systems, they also use libraries which have arrays. And these programs, again, that are used by these kind of systems, they are of parametric nature. That is, the data structures they use, they are in general unbounded. If you look at the program itself, when the program is embedded in an application, the parameter is instantiated based on the model, right? And so let me take an illustrative example of a program that goes into these kind of systems. So here I've shown a program func that takes an array A of parametric size n, and the program does something. I mean, the logic is not really important for the time being, but you can notice that it has branch conditions and loops and so on. I'll denote such programs as Pn. And now, given a precondition denoted as phi n, which talks about the input for the program, I want to establish a post condition denoted as psi n that must hold after the program terminates. Right? And notice that the pre and post condition are also parametric in n, just like the program. And so this problem is formulated as a Hoare triple, where if the precondition holds on your input and if the program terminates, then you want to check if psi n holds. And I want to do this for all possible values of n greater than 0. Okay. And over the past couple of days, we have been listening to people like Sharon and Deepak and Hari and so on. And they have already told us that, the classical methods such as Hoare logic-based reasoning techniques that use invariants, they face a lot of challenges. So here for this kind of programs that have arrays, you require quantified invariants, and generating this invariance is really hard. Then there are other techniques such as abstraction-based techniques. But the main challenge with those kind of techniques is to get the abstraction right to be able to prove the given post condition. Sometimes they land in imprecision, or they continue trying to find one. Right? So this is where I was trying to look at this problem from a very different aspect. As to, I do not really want to go for coming up with a new technique to generate quantified loop invariants, and I do not want to come up with another technique that does abstraction. And so we said that, how does one go about approaching this kind of a problem? And because we are in a parametric setting, the main thing that came to us is that we want to prove this property for all values of n. And so can we use induction somehow to prove the given post condition? Okay. So let me take you through this technique that I call full program induction. This is a very different paradigm. I'm not going to use inductive invariants. I'm not going to abstract properties, but I'm going to induct on this entire Hoare triple via this program parameter n. Okay. So we all know induction. The first step will perform the base case, and I'll fix this n to a constant value. Symbolically here I have denoted it as 1. So what happens when you fix n to a constant value? All your arrays are of finite length. Your loops, they run for finite number of iterations. Now suddenly you have a finitized program. And even your pre and post conditions are over finite number of elements of the arrays. This you can feed to a model checker, and or you can compile this Hoare triple into an SMT formula and ask an SMT solver. If the solver says the base case does not hold, then it's a true counterexample that you have found, and you can tell the user that there actually is a bug in your system. Right? Once the base case succeeds, as per our mathematical induction, you can assume an induction hypothesis. And for our case, the induction hypothesis is the entire Hoare triple, which is phi n minus 1, pn minus 1, psi n minus 1. Okay. And the next step is induction step, and that is where the Achilles heel of these kind of techniques lie. And that is something that that is the place where I try to do the contribution. So if you are trying to do the inductive step over here, you need to compute the difference between this program pn minus 1 and the program pn, and whatever the computation that is remaining, if you perform that computation, then you land in the state that satisfies psi n. I'll denote that computation as a difference program delta pn. Okay. And the second thing you need to do is you need to relate this precondition phi n with this precondition phi n minus 1. That is where I come up with this formula delta phi n, or the difference precondition. And whenever the given program pn minus 1 does not affect any of the variables in the difference precondition, it can be assumed as a precondition for this difference program. Okay. So simple way of thinking. So here, a simple way of thinking about this is that you want to decompose program pn in a way that it's semantically equivalent to the program with pn minus 1 composed with the difference program. That is a stronger requirement. The only requirement I have is that the truth value of the given post condition should continue to hold. They need not be semantically equivalent, because I may not care about certain variables. Right. So now, if you see here, there are two Hoare triples, and the truth value of this first Hoare triple comes for free from the induction hypothesis. So in the induction step, you only need to prove the Hoare triple in the difference program. And the hope here is that if the difference program is significantly simpler as compared to the given program pn, then you have really simplified your verification step. Right? And I'll just take an example to show how the difference program comes out. In a lot of cases, the difference program is indeed loop-free, and that is where the induction step is significantly simpler as compared to proving the original goal. Okay, so let me take an example. So here I have a program pn, which consists of 3 sequentially composed loops, and it operates over an array A. So in the first loop, it's trying to sum up the value of A in variable S. In the second loop, it's updating another array A1 based on the value of A and S. And in the third loop, it's again trying to take the value of S and add the value of A1 to S1. Okay. And I really want to compute the difference program for this program. And so for Pn-1, I'll just rename these variables so that I can distinguish the variables in program Pn with the variables in program Pn-1. So I have a suffix underscore nm1 attached to all the variables. Notice that the loops, they were iterating from 0 to n. Here they iterate from 0 to n-1. Right? And so it is easy to notice that if you're trying to take the difference of these two programs, Pn and Pn-1, the missing iteration that does not appear in Pn-1, it will certainly appear in your difference program. Okay. So let me show the difference program. So here, the first line itself is the iteration that was missing over here, right? Then for the second loop, certainly again, the missing iteration is there. So that I have shown in blue line over here, that the iteration that was missed, you have to do that computation if you want to lead to the same state that the program Pn lands into. But notice that there is another loop that appears over here that says that because you are reading from variable S in program with parameter n, and you are reading from variable snm1 in program with parameter n-1, they have different values because S reads from snm1 and it has some more updates going in there. So you need to rectify the value of A1 in comparison to the value that was computed in the program with parameter n-1. Right? So that is why this loop appears over here, and that it tries to rectify the value of A1. Similarly here, S1 was reading from S, but in Pn-1, it was reading from a slightly different variable. And so there again, the rectification has to be applied. And same thing holds for this loop, because you are reading from A1, whose value was rectified, you need to rectify the value of S1. Yeah. Yes. Yes, if you run Pn-1 followed by delta Pn, you should land in the same state as program with parameter n. Right? Yeah. And now if you look at this program, okay, so here, this loop can be easily summarized. Right? And once you summarize this particular loop, you'll notice that the A1 is not really required, it is not being referred to. And so those kind of simplifications you can do to ensure that your difference program indeed turns out to be loop free. So here I have accelerated the second loop. And for this, accelerated the third loop, and the second loop, you can just slice it off. Okay. And so now you can see that instead of analyzing Pn, if I need to analyze delta Pn, it's much simpler, because here you had 3 loops, here you don't have any loop. Okay. So let me add pre and post conditions to this program. Okay. So it turns out that computing this difference program is, I have a principled way of doing this. I'll not go into the detailed steps, but it's a sound approach. You can look up the details in my thesis or the papers cited thereof. No, we do not give any such guarantee. In fact, the thing is that this technique is re-entrant. If there is a loop in the difference program, you can feed the precondition, the difference program, and its post condition again to the same technique, and it'll do induction on that difference program to prove the inductive step. So you can recursively apply difference computation until a point where either your difference program is really simplified and you are able to prove the property, or that you are not able to progress any further. That may not terminate. I do not give completeness guarantees. For a class of programs, we have an algorithm that can indeed generate a difference program. Yes. But for a class of programs. So just you saw that, given a program with parameter n and a program with parameter n-1, I need to figure out how many iterations I had missed. And to be able to statically figure out the number of iterations that I had missed, I need to know that part. So I restrict programs such that I am able to get that information. Yes, there is a grammar. I have not flashed it here, just for the sake of time. But yeah. So just that question. Yeah. Huh.
Can you keep chaining this, or do you have something like?
So I can keep chaining this, but I have a lot of heuristics. So for example, I can now apply summarization, which I did for the second loop, or k-induction kind of a technique where I just summarize a loop, or I can apply slicing so that, you know, most of the loops, I get rid of most of the loops in the difference program. Yeah. Yes, yes, you can recursively apply the technique to prove the inductive step. So I do not give guarantees whether it will indeed become identity. Yeah, because verification is in general undecidable, so that kind of a guarantee cannot be given. If delta becomes you know, identity, that is, if your difference program indeed turns out to be loop free, then an SMT solver will indeed be able to discharge the, as long as it is in the theory of SMT and it terminates. So there are two places from where undecidability creeps in. Yeah, yeah. Okay, so here I have taken a precondition for this program, which says that for all elements of array A, the value is 1. And if you run this program at the end, you will notice that S1 takes this value n into n plus 2. Right? And so I'll just use the same difference program that we computed. So in the inductive step, I have computed a difference precondition. So difference precondition just says that, you know, what is the assumption on the last element of the array. And I'll take this in minus 1, which is substituting n with n minus 1 in your post condition. It is coming from the induction hypothesis. And now this is something that I'll feed to an SMT solver after compiling it into an SMT formula. If you notice here, there is a variable s underscore nm1, which is not really qualified. And so SMT solver is not able to immediately discharge this assertion. So that says that you still need to strengthen the pre and post conditions. And that is something that I do in this technique. So if you are not able to discharge the inductive step immediately, you try to infer a precondition for this formula. So that is something that I've done here. It says SNM1 is n minus 1. I infer such preconditions by propagating this post in a backward manner, seeing that what indeed holds. I can also guess these kind of predicates using some tool. And once you assume this kind of a predicate, you have to also assert this, because we are in an inductive setting. Whatever you assume after n minus 1 iterations, you have to also prove that it indeed holds after n iterations. And now if you feed this to an SMT solver, it says that this indeed is a valid thing. Yeah.
You also have to prove this for the initial.
Pardon?
You also have to prove this assumption for the case.
I have to check the base case for this assumption. Yeah. Pardon?
It has to be possible.
So each time you apply this differential, your n will increase by some value. I think 1.
Okay. So I never do n minus 2. That's
right. Right. Yes. Yeah.
Right?
Yeah. Okay, so this technique, I implemented it in a tool called Vajra. We had submitted to Takas, and the artifact was accepted. You can try out the tool over here. I have evaluated it on more than 200 programs and compared it against some of the state-of-the-art verification tools. So I was able to verify a large class of programs as compared to, I'll just show in comparison with other tools. But there are cases where I was not able to generate the difference program. There were even cases where the given program had some nonlinear expressions that the SMT solver was not able to handle, even when I had a program which did not have loops. So here is a detailed breakup of the benchmarks. And you can already see that I was able to do a lot of benchmarks, whereas the other tools struggled. A detailed version of this work appears in STTT. That is where you can check it out. And for unsafe benchmarks, again, I was able to catch the bug in most of those cases. So here, when the base case fails, I report that it has a bug. I think most of the other tools were also able to catch the bug. And in terms of time, so this bottom line is for my tool, Vajra, and the other lines are for other tools, VIP, Variabs, Booster, Wafer, and Freecon. Because this is an inductive reasoning technique, I do not really have to infer invariants, or I do not have to really iterate trying to compute the abstraction that really works for that assertion. I can do it really fast. and my difference program computation technique is it's not an iterative algorithm, so it doesn't really take too much time. For certain benchmarks, I had to really apply the technique recursively. That is where it takes some time, or in certain cases, this SMT solver took some time. Otherwise, it's purely like flat line. And same is the case for unsafe benchmarks. I think for other tools also, in case of finding a counter example, they're also really fast. Okay. So I extended this work. So it so happened that computing this difference programs, sometimes there are loops that turn up in the difference program. And I said that I mean, while it indeed helps for a large class of programs for proving the post condition, I do not really want loops to appear in my difference program. Can I do this inductive reasoning using just the peeled iterations of all the loops in the program? Okay. So I'm saying that this difference program, it should always be the peeled iterations. And that's it. I do not really want to, summarize or accelerate the loops. I do not really want to slice them off. By default, the difference program is just the peeled iterations. And that is where we came up with a new algorithm for computing, for doing this inductive reasoning. But now the thing is that I do not have this program Pn-1 for the composition. It's a slightly different program, Qn-1. And so this induction hypothesis now does not really come for free. Okay. So by the way, I hope you realize the fact that in the previous example, when I proved the assertion, I did not use any invariants and there was no abstraction that was used, right? So here is an attempt to create an,
You had assumptions. Those were kind of indicative strength.
They are inductive strengthenings, yes.
Still, somehow manage to figure them out.
I still have to figure them out, yes. But that, yes, but they are not loop specific invariants. So even if you have 100 loops, I may have to strengthen just once. And the predicate that I'm using over there need not be loop invariant for any of the loops. Okay. So yeah, this is an attempt to bring back, some of that inductive reasoning, some of the reasoning that is done by invariants. And so now I'm saying that because I have a different decomposition of the program Pn into programs Qn-1 and peel Pn, right? I want to use the information that was coming from the induction hypothesis. So I'll relate this program Pn-1 with this program Qn-1, and I'll infer relative invariants or relational invariants, so you can call them. And I'll use such relational invariants to use this post condition over here, psi n-1, to infer the post condition psi prime n-1 for this program Qn-1. And so that is how you can leverage the information coming from the induction hypothesis. Right? Once I have this psi prime n-1, again I can perform the inductive step on this whole triple shown over here, and then prove the given post condition. Right? And notice that once you have these kind of relations, if you are inferring facts that are preconditions to this peeled program, they must be asserted after n-1 iterations of the original program. And so that is where this guy psi prime n-1 comes into picture. That you have, if you infer predicates, they will be after the program Pn-1 or psi n-1, and they have to be translated via the relational invariants that you have inferred. Okay, so this work appeared in CAV'21. Yeah, so again, I created a new artifact for this. This was a Docker fully enabled by a Docker image. You can check out the artifact over here. And I have compared it on more than 300 benchmarks. Most of these benchmarks were taken from SVComp competition, as well as a lot of benchmarks came from some of the industrial code at TCS. They were adapted from the industrial code at TCS. I've compared it against Vajra Variabs and VIAP. So Variabs and VIAP have been the tools that have won several rounds of the SVComp competition in the past. VIAP was the winner in 2019 for the arrays subcategory, whereas Variabs has been constantly winning it. A tool from TCS Research. Yes. Okay. So this is the detailed breakup of the benchmarks, where I had 110 benchmarks, which were standard array operations. There were benchmarks which had branch conditions which were affected by n. So computing the difference program was really hard. That is where Vajra really struggled. Then there were benchmarks which had nested loops, where other tools struggled a lot more. But I was able to do all those kinds of benchmarks. Performance-wise, again, I took a slight hit. I mean, the line in green over here is for this tool Diffie. Yeah, because now the programs are more complicated. They have nested loops. They have slightly complicated pre and post conditions. It does take a few more seconds, but is able to verify a lot of benchmarks that other tools struggle with. However, it is still 10x faster as compared to the other tools that participate in the competition. Yeah. So I hope I have convinced you guys that this is an interesting paradigm to look at. Just by relying on invariants or abstraction techniques, we may not be able to go very far. And that is where I am trying to propose inductive reasoning. It is indeed orthogonal to these techniques. I'm just trying to say that I do not really want to compete with those, but I want to be of use if somebody is building a portfolio kind of a verifier. They should strongly consider incorporating inductive reasoning in their portfolio. And that is what Variabs has done. So I've built these tools, Vajra and Diffie, that are a part of Variabs. And yeah, in the future, I'm trying to extend the kind of programs that I am able to prove. And I'm trying to see if the scope of inductive reasoning can be expanded to other data structures, such as lists or even heaps. Happy to take on questions. Thank you for being a great audience. Thank you for inviting me. Yeah. So RFPI is short for relational full program induction. So here, like I said, I need to figure out relations between Pn-1 and Qn-1. And once I figure out those relations, only then I'll be able to use the information from induction hypothesis to come up with this psi prime n minus 1, which will act as a precondition to the field program. Now the proof of this whole triple doesn't really come for free, because this is a slightly different decomposition. Here, the proof was coming for free from the principle of mathematical induction. Yes.
Very nice question. But what was bespoke about arrays here? You said that what you said is requires that.
Okay, so for heaps, for example, so arrays, it's very clear that it's a linear data structure, and induction is something that you can apply in such cases where you are going to go over the entire part of that particular data structure. So for lists, I think it's not that big of an issue. I just need to figure out whether the SMD solver is geared to handle those kind of things. And while doing this inductive reasoning, I need stronger checks probably to ensure that I do not miss any of the nodes in the list. Right? For arrays, I'm able to check that I'm not going to miss reasoning about any of the elements.
Let's thank our speaker.
Thank you.
Speaker is Suman Prabhu from TCS Research.
Yeah.
Hi everyone, thanks for staying back. This problem is something which I worked on for my PhD thesis, and this comprises of 3 papers. So the goal of this talk is to motivate the problem and explain our setting, and then just give an outline of our technique. And this is done in collaboration with these wonderful collaborators. Deepak was my PhD guide. Gregory has been long-time collaborator, and Madhukar was in TCS research, as well as Venki and Supratika, some of recent collaborators. So the problem that we are looking at is specification synthesis. There are many specifications, and a few of talks in this workshop itself had specifications. So what exactly are the specifications that we are dealing with? So we are dealing with open programs. So these are programs which have post condition, which is given in terms of assert condition. But at the same time, they have function calls, but we do not have definition of this function. We know its signature, we know what are its input and output and type and all, but we do not have the definition of it. So maybe the function is proprietary code, so we do not have its code, or it's not yet developed, or it's too large to do verification. So now, can we find some relational constraint for such such undefined function so that the post conditions satisfy? Right. So again, in terms of what, so we are given this open program which have this undefined functions, and there is a post condition. Can we find quality relational constraints? Because not all relational constraints are equally good. So we want some relational constraints which are useful. At the same time, once we substitute the function calls with this specification, it has to satisfy the post condition. Right. Let's look at a concrete example. Okay, so there is this program which has a variable which is getting initialized in the beginning. There's an unbounded loop, and in each iteration of the loop, the variable x is getting decremented. This is followed by a function f. We do not have the body for this function f, but it is returning an integer variable which is stored in y. The post condition is that the value y should be, the value that is written by f should be greater than or equal to the value that x has at this point. Right. So now, can we find some, what all values this f can return, so that in all executions of this program, we have that x is less than or equal to y. Right. So it could be that y is 42. That is the specification that we write is something like this. So the function name and all its input and output arguments. So there is just output here, which is y, and here it is y is 42. Say f is returning 42. Now x value is, it starts with 19 and just gets decremented. So 42 should be the case, right? But it can also be the case that you can f can return 41 also. Suppose say it is a non-deterministic function. Okay, and now we will look at this particular specification. This is saying that the f returns a value which is greater than or equal to 90, right? Now I cannot kind of extend this specification further. So if I say y f returns 18, then there is an execution. Say for instance, the loop will not get executed. Then x will be 19, and when it reaches assert, 19 will not be greater than, less than or equal to 18. Right. So this is, I cannot extend this further. So this is what we call maximal specification. Right. F is not taking argument, but f is giving some output. So in specification we write both input as well as output as its argument. Okay. Let's look at this program. So here there are arrays now. Arrays are unbounded. The undefined function is in the beginning of, there can be multiple undefined functions, but in this case, the undefined function is in the beginning of the program. So it is setting some values to this a, b, and n. This is followed by a loop, and in loop, the value in array A is getting incremented by the value that this initialization set, as well as the sum of the values in B. Now, since there are arrays, the post condition, typically you need quantified post condition. So this is saying between 0 to n, the value that is there in A should be greater than that value that is there in B. Okay, so now what can be this, this initialization, which is also called precondition, right? So what can be, precondition for this A, B, and n, so that we have this post condition get satisfied, right? I can have something like, say, again, the specification is over pre is over A, B, and n, which is you can consider the A, B, and n are its output. So it just says that n is 0, right? In this case, it vacuously kind of satisfy. Loop will never execute, so the implication will be left hand side becomes false. So the post condition will be satisfied. But if you look at this one, right? So this is again a quantified specification. This is saying that between 0 to n, as long as you have A to be positive, then no matter what the values are there in B, this holds. Okay? So this is the weakest possible precondition or the maximal specification that we can find for this program. Right. Now we saw some concrete cases. Now what are its use cases? Right. So this can be used, for instance, you consider this scenario where a device driver is getting developed. Okay, and say this is a keyboard device driver. And the device driver, it is typically done by a hardware organization, and hardware developer is developing a device driver, and they want to interact with the operating system, they do this using, say, kernel APIs, which is just KIO here. Okay, I mean, again, we know the signature, I mean, what are its input, output, and all, but typically this kernel is written by a different organization, so that they may not give their source code. And even if they give source code, it will be too large to verify this particular device. But this developer has some post condition to verify for this device driver, right? So now what is done now? Typically, what is done in such a scenario is the operating system developer gives something called stub, which is kind of an over approximation of what API can do. Typically, these stubs are just says that everything can be non-deterministic. Okay, so and also writing kind of precise stub is error prone. It has to abstract away all the details and so on. So now, can we come up with specification for this API so that the asset satisfy? That's one thing. And also, if we come up with the maximal one, right? If we come up with the maximal one, then that can be given to the developer. And when developer changes this API, as long as the developer makes sure that the change satisfies the specification, there will not be any regression in the device driver code. Okay. Another use case is, say, in blockchain, right? So in blockchain, it typically happens that you have multiple smart contracts, and smart contracts interact with each other, and typically you will have some smart contracts where they call functions which are called unknown functions. So you will not know at compile time what will be its implementation. This is typically written by some other business, some other organizations, and here also you will have such open programs. Now, can you come up with some specification to these open programs instead of just abstracting away everything and just assigning non-dead to all variables? Okay, and there are many other use cases also. This what we saw was in verification. It could be the program repair also. The repair that has to be found, that can be considered as an undefined function, and then we can try to find the program repair. And once you find the specification, right, so it can be used to generate test cases. You can use the test cases that is generated to check for regression and so on. And the precondition that we saw, right, so that can be used to have a runtime check also, kind of what values that can be given to a particular program. And also, the specification itself gives you some kind of precise and concise manual for the APIs that you have. Okay, the problem is interesting. There are many applications and so on. So what are its challenges, right? So first is complex control flow. The open program can have complex control flow, like, say, loops, recursive functions, and non-determinism, and you need to reason about such complex control flow. The second one is, we saw a program where there was this array data structure, right? Developers typically use such data structure for convenience. So, but then these data structure require some rich logic, which are difficult to reason about, right? We saw a quantified formula, right? You typically need quantified formulas for precondition, post-condition, or to reason about loops and so on. So now, how do you reason about such quantified? It's typically difficult to reason about quantified formula. At the same time, the search space of specification is quite large for quantified formulas. The second one is, you have come up with, you face this difficulty and you have overcome these difficulties and you have come up with a specification. Now, how do you prove that is a maximal specification? And third is, the fourth one being, your technique, right? There are so many different programming languages. How can you make sure your technique works over these different programming languages? So the key ingredient in our, we can address these challenges, and the key ingredient in that is constraint horn clauses. So constraint horn clauses are a logical intermediate representation, and many researchers in program verification and have found it to be a suitable intermediate representation to have a program verification problem. And there are many front ends for constraint horn clauses for Java, Rust, C, C++, and also different kind of programs can be represented by constraint horn clauses as well. Right. So I will not go into details of constraint horn clauses. Just to give an example, the program that we had earlier, right? So that can be represented by 3 constraint horn clauses here. This in the beginning there are universal quantification that I've just made it implicit. So the first condition is saying that the initial condition that is there, right? So that there is loop. So loop is represented by a predicate in here, and the function specification is represented by another predicate, say f. Now, in these three CSS, the first one is saying the initial set of states should be there in the inductive invariant, and this is saying that the inductive invariant has to be inductive with respect to the loop body, and this is saying that once you get some states from inductive invariant and then the functional specification, these two, right? So these two should imply the post condition. That's okay. So now a solution to CHC system will be finding an interpretation for these uninterpreted relation which make each of these implication valid. For instance, so you can see this is a solution. So for instance, in would be x is less than or equal to 19 and y is equal to 19. Okay, so this is, I mean, you take my word, so this makes each of this implication valid. So we have been looking at how do we solve CHCs over a few years, and we have different kind of techniques to solve different kind of CHCs. But the issue with this the CHC solving is that it can generate something called vacuous solution for if we kind of represent the specification synthesis task as CHCs. For instance, we can have say invariant as true and f as false, right? So it makes each of this implication valid. Okay, you can see it makes this vacuously valid, and true is makes these two implications valid. Right, so we do not want such vacuous solution as specification false, right? So what does it mean to be f to be false, right? So it's just saying that you enter f, then if you do not terminate, then the post condition always goes, right? So we do not want such specification. But can we restrict such vacuous specification? This we can do to a certain extent, but then we will not be able to get maximal solutions. For instance, I can get something like y is equal to 19 and x is less than or equal to 19. Right? So this is a non-vacuous. I mean, it's better than the previous solution, but still it is not the maximal one. It still doesn't give you as less constraints on the function as possible. The undefined function as possible. Finally, we can get this non-vacuous and maximal solution. This is what our techniques try to do. Trying to get this non-vacuous and maximal solutions. Right. What do we mean precisely maximal solution? So the idea is you have this, you consider maximal over some subset of these uninterpreted relations. So the idea is if you want to a solution is maximal, if say you want to strengthen, if you want to weaken one of the solution, then you have to strengthen another one. Okay, so this is what these equations are. So fine. Okay, so we have this encoding of the problem. Okay, and now how do you find these maximal solutions? So we have this algorithm framework called infer check weaken. So the idea, I mean, this has been implemented, and we have 3 papers over this for different kind of programs. Say we do maximal specification synthesis for integer program, and then weakest precondition for deterministic array programs, and weakest precondition for non-deterministic array programs. So what is this infer check framework, right? So the idea here is this. So let's break this inference in the maximal specification synthesis task into 3 modules. The first one is it takes the input CHC system, which is a specification synthesis task, and it will give you a specification along with the specification being valid, which is the inductive invariant, the proof for specification being valid. It gives you a solution to CHC system, but there is no constraint on inference for there's no hard constraint on inference to get maximal solution. Okay, so there's just a soft constraint that if possible you try to get maximal specification, but otherwise it's okay. Right, so this particular the solution that we get from CHC, this is passed to this maximality checker. So the maximality checker tries to check whether it is indeed a maximal solution. Is there possibility of getting a different solution for this? If it is, then it will be returned to the user because it's a maximal solution. Otherwise, it will give some kind of feedback to this third module, weakening. So weakening will take this feedback and uses some heuristic to get a candidate weakened specification. This is passed to again maximality checker, which will again which first tries to validate it by constructing a new CHC system and then using the inference module itself. And if it is the case, it is weakened, I mean, it is a weakened specification, then by construction, there is some progress in this iteration. So we'll go to the next iteration. Again, the maximality checking happens and this continues. Okay. Right. So yeah. Right. Yeah. Of course. Yeah. I can go directly to infer also. Yeah. That's also fine. There's no need to go to maximality checking. Yes. That's right. So inference model. Right. So of course we can use some of this existing CHC technique, but then as we saw, it can generate vacuous solutions. So we do not want such solution. So we give different kind of CHC solving techniques. So the overall the idea is to enumerate solutions and then check whether they are indeed solution to the CHC system using an SMT checker. So again, the search space could be very large and so on, right? So once we enumerate a candidate solution, then we also try to improve upon that solution if it fails the SMT check. Okay, so this we do something using something called backward and forward propagation. So for this, we use the structure of CHCs. For instance, say we had this CHC, right? So the last CHC that was kind of implying the post condition. Suppose say this CHC fails, as in the interpretation that you give to invariant and F, that doesn't make this CHC valid. Okay, so in that case, we try to find some new specification to this in and F, which kind of strengthens this so that at least this particular implication becomes valid, right? So for this, we use something called logical abduction. So if you're aware of it, it's fine. Otherwise, it's fine. Okay. Then then of course there are other type of CHCs also. The first CHC that we saw, where you on left hand side you do not have anything, right? So you just have some constraint on left hand side, right? On the right hand side, perhaps you can try to weaken it, right? So this is something which we call forward propagation. So this this inference algorithm at a very high level does this, but again the solution could be in different kind of theories, right? So linear, integer, arithmetic, and quantified for formulas for arrays and so on, right? So we give different kind of techniques to do this. So this is one of our contribution. Then the maximality checking itself, right? So to prove maximality checking, we need to prove that if I add any more point to the existing specification, it will not be valid henceforth, right? So this we give based on different kind of programs that we find. First is we just encode it as some quantified, existentially quantified formulas, and then ask an SMT checker to get this for integer programs. Then in other two programs, so we encode a new CHC system such that if a solution to that CHC system exists, then the current solution is either maximal or non-maximal. And finally, the weakening step, right? So in the weakening step, so we automatically construct a grammar using syntax guided synthesis, and then using the feedback that was given to us. And this grammar, this whatever candidate that we construct here, that is again sent to the infer, and then infer will check whether it's a valid candidate or not. Okay, so this is very high outline of the techniques that we have. There are many details inside, so I'll not go into this. But just to give an evaluation, so what we have done is we have built a tool called HornSpec. So this is based on our previous work, and this takes as input CHC system and gives this maximal solution. And we evaluated this on different kind of programs from different computation and some pre-works. So the integer ones, right? So integer ones, our tool itself had this syntax guided synthesis as well as an SMT based solving. So this can give us non-vacuous solution. But what we found was the inference algorithm was substituted by this our own algorithm as well as syntax guided synthesis and SMT algorithm. Right? So what we found was these two algorithms was not able to give as many maximal solution as our tool does. The second one is, so why are we doing, I mean, why are we getting so many maximal solutions? So the main reason being that our algorithm, the inference algorithm, right? So that was giving us this maximal solution in almost maximal. So you can see this is the number of iterations it took us to get maximal solution. So you can see in most cases, in one iteration itself, we had this maximal solution. Okay? And it was proved to be maximal as well. Then with the array programs, right? So we were getting, we had these two different, we have two different works, one for deterministic array programs and another one for non-deterministic. In deterministic, we find that, our tool can generate many than the state of the art. And also, it was able to prove many of this to be weakest precondition. And all of these are quantified formulas over arrays, and the post conditions are also quantified. Then for non-deterministic, it can, again, it's non-deterministic. There's not much support for non-deterministic programs. So this is ours. Ours is one of the tool that can generate non-deterministic for weakest precondition for non-deterministic array programs. So you can see that the number of preconditions that were generated, it generated all of them, but it could prove only it could prove along at least 90% of them. Then manually we found that the rest of them were also maximal, just that the maximality checking was not able to decide that. And of course, so we gave these the preconditions that were inferred, right? So we gave this to some of the state-of-the-art invariant inference tools, and we find that our tool can find all of them, but though others were not able to find as many as our tool does. Okay, so in conclusion, so the specification synthesis problem. So this is an important problem that has many applications, and so we have come up with this framework called InferCheck Weekend. So this is a kind of flexible framework in the sense that the inference algorithm can be exchanged with different kind of inference algorithm. Just that it has to take an input CHC system and then generate a solution to that, and then the maximality checking also, right? So depending on the program, we can have different kind of maximality checking. Then also it's a reliable framework in the sense that the specification being valid will give proof in terms of inductive invariant, and specification being maximal also will give some maximality proof in terms of programs. And finally, yeah, so if you are interested in this problem and would like to know more about this or collaborate, then you can always
We have time for a few questions. All right, let's thank the speaker again. With this, we end RHPL 2020. Thank you.